acceptance, inviting the strangers to become friends and transforming unfamiliar spaces into heavens of belongings. I invite Dr. M. Pallikonda Rajashekaran, Director R&D, for the welcome address.
Ladies and gentlemen, esteemed dignitaries, respected guests, organizers, fellow research scholars, distinguished faculty members, member of press and media, a warm and joyful Happy New Year 2024 to each and everyone, and very good morning to you all. It's truly a honor and privilege to stand before you in this auspicious occasion, representing our Kare family as we embark an inaugural ceremony of pre-conference National Symposium on Advanced Mathematical Methods of the 10th edition of International Conference on Mathematics and Computing, Icmc 2024. At this juncture, I extend a heartfelt welcome to our chief guest, Dr. G.P. Yuvraj, the former director of Ramanujam Institute of Advanced Studies in Mathematics at the University of Madras. Your presence adds immense value to our event. We are very grateful to you on your participation, sir. Welcome you, sir. I would also like to extend a warm welcome to our guest of honor, Dr. S. Ponnuswamy from Department of Maths, IIT Madras. Your expertise and insight are invaluable, and we are privileged to have your grace this occasion with your presence, sir. Welcome you, sir. I would like to extend a warm and sincere welcome to our respected Vice Chancellor, Dr. S. Narayanan. His unwavering support and continuous presence since the inception of this conference have been instrumental in making this event a grand success. We are truly honored to have your presence and guidance and leadership shaping this trajectory for this conference. I welcome you, sir. I would like to extend a heartfelt welcome to our esteemed registrar, Dr. V. Vasudevan, for this function. Dr. V. Vasudevan dedication to the academic community and his commitment to the advancement of mathematics and computing have been instrumental in shaping this conference into the significant event of today. We are truly grateful for his leadership and contribution, sir. I welcome you, sir. A warm and cordial welcome to our esteemed resource persons for this pre-conference. We are honored to have a distinguished individuals, Dr. Prem Lakshman Das from Society of Electronics, Transaction and Security, Chennai, Dr. Gautam Sekhar from Madras School of Economics, Chennai, and Dabs Chatterjee sir from IIT Ropur, Punjab. Their presence and contribution undoubtedly enrich the academic discourse and enhance the value of this conference, pre-conference. We welcome you, sir. Certainly, we welcome Dr. P. Deebalakshmi, Dean of School of Computing. Through her support, this pre-conference and also the international conference has come to this level. Welcome you, madam. And certainly a warm welcome to organizing chair, Dr. Yagna Narayanan. We acknowledge and appreciate the Yagna Narayanan's pivotal role as a main driving force behind all the planning and execution of this conference, pre-conference and conference. His dedication and meticulous planning have been crucial in bringing together the researchers, scholars, and experts in the field of mathematics and computing. Dr. Yagna Narayanan's efforts have undoubtedly contributed to the seamless organization of this conference and ensuring its success and impact. A warm and appreciation welcome to Dr. Karupasamy sir for his continuous support from the beginning in making this conference a grand success. His commitment and guidance undoubtedly played a significant role in supporting the Yagna Narayanans and the entire organizing team. We welcome all the organizers and esteemed faculty members, dedicated research scholars, and members of press and media who have grasped this occasion with their presence. Every day is a chance to get better to shape us in various multi-dimensional directions. These 6 days, which has to be filled with unconditional inspiration, joy, and promise for a bright future to utilize the knowledge transferring platform on the core of mathematics approaches towards various soft computing techniques. So knowledge grows exponentially when it's shared. As per the words of Martin Luther King, taking the first step in faith, don't bother about, you don't have to see the whole staircase. Each step will be created on the right time. So everybody has rightly taken the first step towards the action of knowledge sharing by joining our conference. Rest assured, everything is going to be on the top notch to climb the goals. The hardest part is the starting, and once you get started, you will find the rest of journey much easier and comfortable. Let us all have the great time in the next 6 days, and thank you for this great effect. Thank you.
Thank you so much, sir. A symposium is the melting pot of diverse minds, where disciplines converge and the fusion of perspective sparks the flame of innovation. I invite Dr. V. Egnanarayanan, Organizing Chair of ICMC 2024, to share the insights and thoughts about the symposium with us.
Very good morning to one and all present here. After a nice welcome address by our beloved R&D Director, Dr. Pallikonda Rajashekar, it is my privilege and duty to say a few words about this technical symposium on advanced mathematical methods. I once again, along with our Director R&D Research and Development, I welcome all the dignitaries on the dais. A main instrument behind this success of organizing this symposium and following this conference, full credit really goes to our Honorable Registrar Dr. V. Vasudevan sir. It is he who really brought me into the limelight. I have been working in this organization from 2021, and only after 3 years, of course, I am busy with my research project. Even at the time of joining, our registrar offered me, what do you want, we will provide. And I said, sir, please allow me to complete my project. Then I will look into other responsibilities. So then he called me, why don't you organize a conference? I said, okay, sir, now this is the time I will take, and I will organize within a year. So this I told him in 2022. After that, it is an interesting beginning for me. I was really searching, and I could not come to a conclusion whether we should organize an international conference on our own, or shall we organize a popular series of conferences happening throughout India. So when I was in double minds, it is our honorable guest of honor today, Dr. S. Ponnuswamy sir, Professor of Mathematics, IIT Madras, who suggested to me that you should organize, why don't you organize this ICMC series of conferences? Then I said immediately yes. Then he suggested me, why don't you organize one pre-conference symposium also, along with the Ramanujan Mathematical Society, because he is a president. He is a president of Ramanujan Mathematical Society. So he promised all support from Ramanujan Mathematical Society, and he said, he motivated me. Then Cryptology Research Society of India and then team to organize this 10th edition of International Conference on Mathematics and Computing, and before that a pre-conference on National Symposium on Advanced Mathematical Methods. So the real credit actually goes to our Dr. S. Ponnuswamy sir for suggesting, giving this valuable suggestion. Then he asked me, why don't you do a small research and tell me what are all the topics that has to be fixed for this advanced mathematical methods. Then I did some research and then found that in this southern interior part of Tamil Nadu, as of now, or at least in the past 1 or 2 decades, expertise is lagging in analysis, number theory, and cryptography. So when I suggested, okay, very good, it very well syncs with our Ramanujan Mathematical Society's primary objective. So you have said number theory. So number theory is indirectly being supported by, without analysis, there is no number theory. So he is very enthusiastic and supported me in identifying the resource persons. So with his effort, he is a real man behind success. When our beloved registrar is the man behind the whole initiative, it is Dr. S. Ponnusamy sir who is the man behind all success. I have just played, I am only a tool in their hands, that's all. I did not assume anything big on my part that I have done this, I have done that, no. They are the real motivational and inspirational factors and played a major role in making this event happen. After that, it is my responsibility also to thank our management, our Honorable Chancellor Sir and Pro-Chancellor Madam, and our beloved Vice President Dr. S. Sasianand Sir. They wholeheartedly supported with and magnanimously given enough grants to make this as rich as possible. So they have given me full freedom, whatever you want, you please ask sir, we will provide. Money is not at all a problem for us. You go ahead, you plan, we are behind you to support. Whatever you want, we will provide. That is why we are seeing here a rich show. And I really thank our top management for this full wholehearted support. And then from that day onwards till now, it is our Honorable Vice Chancellor Sir's encouragement and support periodically. Whenever I was in need of suggestions, he is really there to offer it because of his rich experience with number 1 institution in India, VIT. So he has served VIT for more than 35 years and he brought with him rich experience which he shared with me, and with his valuable suggestions and support, I have made this happen. We have made this happen. And then last but not least, it is my privilege to thank our Dr. Deebalakshmi, School of Computing, Dean School of Computing, and Dr. K. Karbasamy sir. These two they are my right and left hands for this entire conference and symposium. Without their help, and this would not have been happened. And mathematics department and SOC department faculty members have put in lot of their hard efforts. Our R&D sir was telling that I am giving messages at 2 p.m., 3 p.m., 4 p.m., 11 p.m. like that, 2 a.m., 3 a.m. But my team members also did not sleep for the past, at least for past 4-5 months. So with all our collective efforts, we are now standing before you for this national symposium. Then if I just say these things and go, it will not be complete. And so let me say a few things about the topics chosen for this national symposium. Real analysis and complex analysis. So analysis, so we have arranged here lectures on both of these topics. All of you know very well that traditionally these two subjects, real analysis and complex analysis, are separate subjects. So if one is taught in one semester, the other will be taught in the other semester. They will not be taught together in any semester. Thinking that these two are two separate entities. But it is not so. There are several intimate connections between these two subject areas. For example, I just give two interesting examples. The Rees representation theorem and the Hahn-Banach theorem are used. They are permit us or allow us to guess Poisson integral formula. They combine, they form a team in the proof of Raj's theorem. They combine with Blashy's theorem on the zeros of bounded holomorphic functions to give you a proof of Munch-Zizas theorem that concerns with approximations on an interval. This is one nice example of an interconnection between real analysis and complex analysis. Similarly, L2, capital L2 is a Hilbert space, and it is used in the proof of Radon-Nikodin theorem, which leads to a nice theorem about the differentiation of indefinite integrals, which in turn again leads to the proof of the existence of radial limits of bounded harmonic functions. So like this, there are several interesting connections between real analysis and complex analysis. Our experts have come here. Dr. G.P. Yuvaraj, our chief guest today, is a doyen in real analysis. So he will give more interesting connections between these two subjects. And then our guest of honor, Dr. S. Ponnusamy sir, who is a specialist in complex analysis. He will also deliver a lecture. In between, he offered, amid his busy schedule, in this he wanted a window. So I have to create a window for him, and he will be very happy to give a lecture for 1 hour on complex analysis as a bonus to our already pre-planned schedule of this National Symposium on Advanced Mathematical Methods. Then, analytic number theory. Our Tapas Chatterjee from IIT Ropar has come here. He is a specialist. So when we invited him, he asked, there are 3 types of number theory: algebraic number theory, analytic number theory. Which subject you want me to lecture? So he is a specialist in both. And the transcendental number theory is the 3rd one. Then I said, sir, please, should you prepare your talk on analytic number theory? Because almost all of us have already done one course in our UG or PG in analytic number theory by Apostol or Davenport's multiplicative number theory. But a coherent treatment method to traditional subjects like real analysis or complex analysis or measure theory or topology seems to be somewhat missing in the textbook treatment of analytic number theory. It is only an illusion. How to overcome it? So, one loud thinking which I get is, if the humanity were collectively more intelligent, if the humanity were collectively more intelligent than it is, then an appropriate treatment of analytic number theory should first start with the proof of generalized Riemann hypothesis, and then go on to prove other results predicted by pretending that the distribution of prime numbers is random. Because people are trying very hard to settle Riemann hypothesis that the roots of the equation zeta of s equal to 0 lie on a straight line in the complex plane precisely at the real part of s equal to 1 by 2. It has been found to be correct and checked for 15 into 10 power 8 integers. But for any given integer, whether this accepts a solution or not is still an open problem, and it is being carried from to 21st century also. And hopefully some mathematicians will emerge in this century to settle that. And if that is settled, it will shed light on many of the intriguing problems hanging around the distribution of prime numbers. And then finally, cryptography. Cryptography, we all know very well that it is a hotly pursued topic, very hot topic, and very enthusiastically pursued by both mathematicians and computer scientists. Both of them wants to be experts in cryptography because it safeguards personal identity, confidential data, to authenticate identity, to establish trust between servers, and so on. It is a critical infrastructure. Cryptography is a critical infrastructure because sensitive data, security of a sensitive data relies on cryptographic solutions. So if you want to acquire expertise in cryptographic solutions, then you need to be fluent with the fundamentals of analytic number theory. And if you want to be conversant with analytic number theory, then you need to have a better understanding of the basic subjects called real analysis and complex analysis. That is why the topics of this National Symposium is carefully interwoven around these topics. So with the blessings of Almighty,
Dr. Tapas Chatterjee, an accomplished associate professor in the Department of Mathematics at the esteemed Indian Institute of Technology, Rupa. Dr. Chatterjee holds a distinguished academic background, having earned his doctoral degree from the prestigious Institute of Mathematical Sciences in Chennai. Dr. Chatterjee's research endeavors are centered around various facets of number theory, showcasing his deep-seated commitment to advancing mathematical knowledge in this domain. His expertise and contributions have not only been recognized nationally, but also have gained international acclaim through his collaboration and affiliations with esteemed institutions across the globe. For those who are interested in exploring fascinating world of mathematics under Dr. Chatterjee's mentorship, the opportunity for summer internship awaits at IIT Rupa. Dr. Chatterjee starts a beacon of academic excellence, contributing significantly to the field of mathematics through his research, teaching, and international collaborations. We are honored to have him as a distinguished participant in the symposium, and we eagerly anticipate the insight and knowledge he'll share with us today. The spotlight is yours.
Thank you very much. Okay, okay. So should I stay here? It's fine? Okay. Okay, thank you. Do you need this or without this is okay, no? I can speak louder. Okay. We are recording the... Oh, this is a little bit... Oh, no, no.
Check. Hello. 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 Check. Hello.
Hello? Hello? Okay. So am I audible now? I think, yeah. Okay. So, hello? I think it's better, right? This is better? Thank you. Okay, so thank you very much, Professor Eknarayan, for inviting me and giving me this opportunity. And this is my pleasure to speak during this auspicious occasion. So I will, in my first talk, I will discuss about something a classical constant and their various generalizations and applications to many problems like division problems and other problems. And this works actually is joint work with one of my former PhD student, Dr. Suraj Singh Khurana, who is currently is assistant professor at SRM University. So today we will speak about gamma. So you can see this rate constant gamma, which appear in something called Riemann-Zeta function. Maybe I will speak about Riemann-Zeta function tomorrow, more details. But let us start with this constant. So gamma is one of the three important constants which appear in mathematics. Probably we have already know this thing. Pi and E. Pi is the ratio between the circumference and the diameter of a circle, and E is the Euler number which appears naturally. Similarly, gamma is also another natural constant which appears naturally in many places, and we will try to discuss about the analytic theories of this constant and the generalization, not the algebraic arithmetic theory. Okay. And if I have time, then maybe I can discuss some little bit more generalized things on this gamma. So let me start about my outline of the talk. So I will give some introductions and history of this, then motivation behind this work, and then we will have our constant which will be motivated by gamma, and finally many more generalizations. So this gamma was actually originated in a work of Leonardo Euler in early 18th century, when Euler was trying to understand the harmonic sums. So I hope harmonic sum you know. Harmonic sums are sums of the form 1 plus 1 by 2 plus 1 by 3 and so on. And we know that these sums is not something called convergent. So Euler was trying to understand that anyway, do you have some kind of finite quantity which one can associate with these sums? And then Euler introduced this notion of something called gamma, which is nothing but you take sum of 1 by n up to x, and then you subtract by log x, and then take limit x tends to infinity. And then Euler showed that this is actually a convergence now, and this is called gamma, is convergence to the constant gamma. Okay. And this was Euler paper. Anyone can read this paper. This appeared in 1734, where he introduced these terms. Okay, so gamma actually appear many places, not only in mathematics. It appear many places. For example, it is so important. You can see that it appear starting from Feynman diagram in quantum field theory in physics, and then appear in Grumble distribution. It's part of a mean of Grumble distribution in statistics. It is also inside the information theory, entropy relations, and chi-square distributions involved with gamma, this constant gamma. It appear in zip law of mathematical statistics also. Many more places gamma you can find out. It is almost everywhere, not only in mathematics, in mathematics, information theory, in computer science, cryptography, physics, everywhere you can find out this constant gamma. So this is so natural. Along with pi and E, we call this is a holy trinity, means the three, like the three God. We have the three main God, right? Brahma, Vishnu, and Maheshwara, Shiva, Lord Shiva. Similarly, we have the three major constants, pi, E, and gamma. But for pi and E, we have more knowledge actually. We know about their nature. Actually, we know that pi and E both are transcendental numbers. For gamma, we have no knowledge actually. We don't know whether it is even rational number or irrational number. But unfortunately, I am not going to speak anything on transcendence theory for today's talk. Today, I am going to discuss on the analytic properties of this function of generalization. So naturally, one can ask that where gamma appear in number theory. And number theory also, there are a large number of places where gamma appears along with the other natural constant like digamma functions, psi, then divisor function, the Riemann functions, this phi n is the Gaussian function, gamma x is the Gauss gamma function. So there are so many functions that has relation with this Euler constant gamma. Let me give you few of those relations. The first relation tells you the integral representation of gamma, and this is due to Barnes in 1903. And then you have the relation, these sums, infinite sum relations of gamma. Then the third one is due to the famous Indian mathematician Ramanujan, who has expressed gamma in terms of integral and both the infinite sums. And there are many more such things in the literatures for gamma. Okay, and for those who are interested to know more about Euler constant gamma, they can read this famous article of Lagarius, Jeffrey Lagarius, and this article contains many more nice identities of Euler constant gamma and their properties. Okay, so let me go quickly about our ideas. Now we will see that why people are more interested about this gamma. So there is something called famous Riemann functions, this zeta s. The Riemann functions is originally defined for real power of that s is bigger than 1, where it is absolutely convergent. But again, one can do something called analytic continuation throughout the whole complex plane. And we see that at s equal to 1, it has a actually simple pole of residue 1. And if you want to define the Laurent X function on s equal to 1, then it has, this is the Laurent X function, Riemann function, which is of the form 1 over s over s minus 1 plus sum over minus 1 to the power k factorial k, gamma k is minus 1 power k. That gamma k are called nowadays Euler-Stieltjes constant. In particular, when k equal to 0, it is the constant term, which is called the Euler constant gamma. Okay. In general, these constants are called the Euler-Stieltjes constant. They do the work of Stieltjes. And then Stieltjes defined in more general, he extended Euler's idea, saying that gamma k's you can write down as the limit of these sums log power k by n divided by n, when n is running till x, minus log x power k plus 1 divided by k plus 1, and then you take x tends to infinity. Even again these sums, actually these first sums, logarithm that sum, this is actually divergent sums, and the main term of these divergent sum is log to the power k plus 1 divided by k plus 1, but one can show that when you take the difference, that sum actually converges to this constant gamma k. So this is famous work of Stieltjes, and nowadays we call it Euler-Stieltjes constant. And then there are several generalizations of this constant which is appear in the literature. For example, this one is due to Briggs first, but we call it Euler-Briggs because Euler-Briggs and Lemmer, 3%, because Briggs introduced this constant, which is kind of something called the partial gamma function. He was actually motivated by a work of Dirichlet. Probably you know that Dirichlet is the father of analytic number theory. The famous Dirichlet was trying to find out the partial sums of zeta functions, and with the motivation of Dirichlet, Briggs defined these functions, something called partial gamma constant, gamma rk, which is now you can take the sums over 1 by n, but not all the integers. You take only those integers which are co-prime to r, which are modulo r mod k. So what does that mean? That means suppose k equal, you fixed a k equal to say 5, and then you are taking r equal to 1. So you will sum over only 1, 6, 11 and so on. So those integers must be modulo r mod k. And then along with the idea of Euler and Stieltjes, Briggs defined those things. And then later Lemmer actually proved lots of properties, analytical properties of this constant. Nowadays we call this Euler-Briggs-Lemmer constant actually. Then what Knopfmacher did, Knopfmacher actually generalized this constant, this Briggs and Lemmer constant, and it is along with the idea of Stieltjes again, and this is called nowadays this Knopfmacher constant, gamma k rq. Now here not only you have you are running over n, which is which is modulo r mod q, you are also taking the k factor here. You can see that gamma k, and this k in this it comes in this infinite sums log n power k divided by n. So this sums. So you can understood from here that the Knobmacher constant is actually coming from Stieltjes constant and Briggs constant. So it's kind of generalizing both the constants. Okay, and this is in this same paper, famous paper Knobmacher, he actually introduced this constant and he showed that they are not ordinary constant, they appear in something called the L functions. Okay, so maybe tomorrow maybe I can also talk about L functions little bit. So, so whoever doesn't know L function, let me tell about L functions are nothing but something called Dirichlet series, like we know power series, right? In something you are writing of the power series of function x, like 1 plus x plus x square something, or 1 plus c0 plus c1x plus c2, something like that. Then Dirichlet series is something we write down of the form 1 by n to the power s, so 1 by a, 1 by 1 by 2 to the power s, 1 by 3 to the power s, and so on. These are called a Dirichlet series, and L functions are nothing but the Dirichlet series, and you can also associate some function f in terms of L series in that. So suppose you have some function, okay, so let me define some periodic functions in the natural number to C, and then what you do, you define L functions at S which associated with f of these forms, f of n power s, n bigger than or equal to 1, and generally it is, you can show that this kind of function is absolutely convergent whenever your real power of s is greater than 1, and you can choose arithmetic functions, you can choose periodic functions, you can define like that. So Knobmacher showed that given a q periodic functions, so periodic means that it takes the value in every q period. So f of 1 is same as f of q plus 1, same as f of 2q plus 1, and so on. Similarly, f of 2 is same as f of q plus 2. For this, if you take the kth derivative of this L function associated with f, such that, so this function exists if and only if the sums are 0, and not only that, this kth derivative, the constant term is actually this constant, gamma k rq. So the kth derivative of L function at 1 is of the form summation fr into gamma k rq. So these constants are so fundamental, they appear as a this expression of derivative of L function at s equal to 1. Okay. Provided that, obviously, provided the sum of f of r has to be 0. If it is not 0, then this function has a pole at s equal to 1, and then obviously you cannot write down of this form. Okay. So this was famous theorem of Knobmacher, and we got motivated by this Knobmacher's theorems. We want to know what about whether we have such kind of results other than s equal to 1. Because you know the Riemann zero functions, the critical region is called the real power of any real number from 0 to 1, and there is a famous hypothesis called Riemann hypothesis that if Riemann zero function has a 0 which is not a real 0, it must lie on the real power of the line called real power of s equal to half. So this is called the Riemann hypothesis. So with the motivated by Riemann hypothesis, we try to understand what about the derivative of L function at other points. So this is my question we ask. Do you have some nice constant which associated with derivative of L function at s equal to some other real number in between the critical strips, say 0, in between 0 and 1, which is majorly not known. And this question actually gives us many results. So let me start with the definition. We named this function as a shifted Euler constant, or you can say generalized Euler constant. I will show that this constant actually generalize all the existing constant, starting from Euler, Knobmacher, Briggs, and everything we generalize in between that critical steps. So so suppose we have these sums hk x alpha rq, which is of these forms, that sum over log n power n divided by n power alpha, when n goes till x and n is congruent to R mod q. Obviously, these sums is divergent sums, it does not convergence, but we want to know what is the main term. When you take in analytic number theory, there is two major things. One is called the main term, one is called the error terms. Now, if we know the main term is quite large compared to the error terms, then we can make main term, the first sum minus the main term can goes to very small as possible. So then we calculate the main term is actually of this form, IRXK, this is the main term, IKX alpha, and then you see that this is kind of nothing but a polynomial in x whose coefficients are log functions. Okay, and hence then we prove that this logarithm, this limit of these functions minus the main term is actually converges, and these convergent values we define is by shifted Euler constant zeta k alpha rq. So you understood the motivation behind our results. So then we showed that this convergence, and then obviously, so let me tell you that the proof requires nothing but something called Riemann-Stieltje. So if we use Riemann-Stieltje integral, the proof is a little bit easier, and obviously we need Abel summation formula and other mathematical induction on K. And then after defining this constant, we prove this theorem which appear in the journal of number theory. And this theorem tells you that for any non-negative integer k and alpha, these sums is actually main term. Main term is IKR, and then you have constant term HK alpha, and then the error term which is big O of log x power k divided by x power alpha. Big O means what? That means whatever the function that is bounded, the mod of that value is bounded above by some constant time log x power k divided by x power alpha, and hence when x tends to infinity, that goes to 0, because log x is a little o of x power any power. So x is always going faster than log x. So when you take x tends to infinity, x is dominating. So log x power alpha goes to 0. Okay, and where this hk alpha is of this form, this integral. And now let me discuss about the properties of our constant. So one can check that this zeta 0 and k equal to 0, this is nothing but the Riemann zeta function, the classical Riemann zeta functions. And then you can have this has some kind of periodic property. So the values when r plus minus q are same, so it's kind of periodic with respect to the period q again. And then if you take the sum of this function over r equal to 1 to q, it becomes the constant hk alpha, which we define just. And there are many other properties. So these properties are similar to some properties of gamma functions due to Gauss, Carl Friedrich Gauss. So so these are the properties which we find out, and let me define the main theorem here. So main theorem, what we prove here, we prove that this constant zeta k alpha q you can express in terms of something called periodic zeta function, which is another very important function in analytic number theory. And we have this following theorem, that zeta k alpha bq is of this form hk alpha over q plus some sign factor minus 1 power k by q, and then the derivative. So this is, you understood, k means the k derivative of the periodic zeta function at the point a by q. A by q is the rational point, q is integer and a is something which is up to q. A is range variable 1 to q with e power exponential function e power minus 2 pi ab by q. Okay, so this was the first theorem, rather second theorem after defining that, and then we can do, so maybe we can skip the sketch of proof quickly because I don't need to define this. And then yeah, so after that you can use a famous identity of Ramanujan, and with this identity, okay, so let me discuss that. This identity of Ramanujan he discovered independently. So he did not knew, I guess he did not knew about the famous Riemann work, Riemann's identity of this Riemann zeta functions, which is more famous. In fact, we know that Riemann zeta function has a functional equations at s equal to half point, which is more famous, but fortunately this identity is actually more useful. this Ramanujan's functional equation is more applicable, and we use the functional equation of Ramanujan, and then we derive that our function when k equal to 0 has a very nice integral representations in terms of Prochemer symbols. So this idea leads us to find out the significance of our constant in terms of both this derivative of periodic functions and the Prochemer symbols. Okay, now let me discuss the connections between the partial zeta functions. We recall that Knobmaker has showed that the constant of Knobmaker, which is a generalization of Euler-Stieltjes constant, is actually coming as a coefficient of derivative of L function at s equal to 1, right? And then we ask whether we can have similar kind of result or not, and then we showed that indeed there are similar results, and this is for this we did something called the partial zeta function. And here is the definition of partial zeta functions. Partial zeta function we define by zeta s rq is summation 1 over n power s, where n is running over 1 to infinity, and n is congruent to r mod q, and this function is again absolutely convergent whenever real power of s is bigger than 1. But I am defining for this the range when real power of s is bigger than 1, but you can do something called analytic continuations that you have learned probably in complex analysis, something called analytic continuation. You can define it for throughout complex plane except for few poles. Generally poles appear at s equal to 1 place. Okay, and then when you take the Laurent function of this function at s equal to 1, and then you see this zeta gamma k rq sitting inside the Laurent function is exactly generalization of Stieltjes constant. And now if you want to take the derivative, then you see that when you want to take zeta s as s equal to alpha, then you see that this our number zeta gamma zeta m, okay, it's not visible here, you can see that zeta m alpha is sitting as a coefficient of these partial zeta functions. So partial zeta functions which we define is actually more natural, more naturally comes with partial zeta functions. So these numbers are, that's why so important, which is linked to the Knobmaker constant. And now immediately, so this sketchup proof also, let me just skip it, we don't need this. So again, so the main idea is actually Riemann-Stieltje. Riemann-Stieltje will gives you the main proof, but I don't want to discuss this proof, let me just skip this proof. Okay, so as a corollary of this, we can attach this function with something called Hurwitz zeta function. So Hurwitz zeta function is defined by this. So zeta s x is defined by sum over 1 by n plus x power s n greater than or equal to 0. And again, one can show that this function is absolutely convergent whenever real power of s is greater than 1. And this is also called the factors of Riemann zeta function. In fact, when x equal to 1, then you can easily prove that zeta s x is nothing but the classical Riemann zeta function zeta s.
So whenever you're speaking, it will be somewhat vibrate. So
Okay.
better.
Yeah. Okay. So with the help of that, we can find out the power series expansion of Hurwitz zeta function at the point r over. So instead of x, if you choose the rational value r over q, then you see that inside that we have our constant here zeta m minus j, that is sitting inside that. Okay. And there are many more corollaries that comes from directly from divisor function and other things that all are attached with our newly defined constant, which is called that Shifted-Euler constant. And then finally, we are interested to find out whether the Knobmaker theorem can be generalized or not, and here is the generalization. So what we will do? So Knobmaker prove it for the point is equal to 1. We showed that for any real values in between 0 and 1, if you take the derivative of the special values of L function, then the constant appear in the expression is not the norm maker one, it is our constant, which we call shift zeta function. You can see that zeta k alpha rq is sitting inside the expression of derivative of L functions. Okay, so this is our main theorems in this paper, which we showed that this constant should naturally appear in the derivative of L functions also. Okay, so now let me discuss some important corollaries that comes directly from this result. For example, you can invert and you can find out that these zeta values are this zeta m alpha, these values are also linked with something called the some function called the function coming from the Dirichlet character. So here the chi is the Dirichlet character mod q, that chi bar is nothing but the conjugate of chi, the complex conjugate. Okay, and then you can find out this function which are appear actually in the Dirichlet characters mod these functions. And then there are several results. So let me discuss one more things that tells about something called the non-vanishing problems. These are also very important problems. People doesn't know many things about the non-vanishing of L functions or not. And we prove that if these special values of our functions zeta k half r by rq is linearly independent over the field of algebraic numbers, then actually this zeta, the k derivative of L function associated with the Dirichlet character chi at is equal to half is actually non-zero, and this is still unknown. These results we know from the work of Dirichlet that L function associated with character chi at is equal to 1 is non-zero, but as it is equal to half we have no idea. But it comes from our results that if we assume this assumption, then these values are also non-zero. So these non-zero results are very important in analytic number theory, so that we showed here. Okay, now let me discuss some applications. So there are various applications you can do it for this newly defined constant. So let me start about a classical problem due to Dirichlet. It's called Dirichlet divisor problems. So Dirichlet studies this divisor function dn. So dn counts the how many divisors are there. For example, if you have say 2, then d of 2 equal to 2. You have only 2 divisors, 1 and 2. For example, if you have 4, then you have 3 divisors, 1, 2 and 4, right? So if you want to know how many divisors are there on an average up to x, then Dirichlet proved that these divisor function, these are called the average of divisor functions or other partial sums. These are actually of this form. The main term is of the form x log x, and hence the average of divisor function is log x, the main term. And then you have some constant term here, 2 gamma minus 1, plus something called the error term. The delta x is called the error terms. So this error term is very important actually. The error term tells you about not only divisor function, it also talk about something called the famous Riemann hypothesis. So if we have a nice error terms, if we can find out the nice error term, we are going to prove the Riemann hypothesis, which is very classical. But unfortunately, these are still conjecture. So for example, Dirichlet himself proved that the error term will be as big as x power half, and then there are many results due to Voronoi, Manda-Kerfoot, and Van der Waals have many results. And so this goes on, Ivanik and Huxley, there are so many results. So conjecturally this number is actually 1 by 4 actually, these error terms, x power 1 by 4, but it is still unknown to us. And then motivated by this Dirichlet's problem, people ask what about numbers which are more than, say divisor means what? You are finding n in terms of factor of 2 integers, right? But if we factor into say k many integers, so suppose we have tau kn, which actually count number of positive divisor of n, which can be written as a product of k many factors, m1, m2, mk. And you want to play the same game, what Dirichlet play, you try to find out the error terms of the partial sums of the new function, tau kn, then what happens? Then the result is known little bit. Then it is known that this function average order actually involve the main term, which is a polynomial is logarithm plus the error term delta kx. And there are many results obviously in the literature. The famous one is that these error terms actually constant, not with respect to the usual measure. the Lebesgue measure will not help you to find out that finiteness of this integral, but you need to define something, another measure. So this is, the measure is du by u to the power 2, so u square. With respect to this measure, you can show that this constant, this error term is integral converges, and this is a constant. Okay, so this is a famous measure of Larvik, and we want to now, motivated by this result, we want to know that whether we can have similar result for whatever constant we define right now, the last is the constant. Okay, so with the help of that, there are many, okay, let me just define many more results which are already in the literature. One result is called Sita Ramachandra Rao result, and Furuga's result, and Tanigama's result, and they studied this kind of constant for more general function. So this is the more general function. This is called delta 2x R1, Q1, R2, Q2. So R1, so you choose all the integer which is congruent to R1 mod Q1 and congruent to R2 mod Q2. So what does that mean? That means, so you are not, right now you are not going to discuss all the divisor. You choose only those divisors which are congruent to 1 modulo some particular integer Q1 and Q2. And then you want to know what about the partial sums. Now again you can show that the partial sums has a main term which come from again the complex analysis, and the main term is nothing but the residues of this product of the functions at is equal to 1, and the proof is also again you need to use something called the Riemann-Stieltje integrals. Okay, with the help of that they have showed that this function has this error term has a bound which is nothing but x to the power 1 by 31 by 416 into log x power something, some constant. This is the so far the known bound, and then what we did, we try to generalize this idea in terms of our constant. So we have defined generalized Euler constant or shifted Euler constant. We want to know that whether these results are there whenever the numbers are in between 0, 1, the real numbers, and we can use some bound or not. And this is our result. So we showed that similar to Larvik results, that error of, you see the error functions delta 2x, the error functions has a converging integrals with respect to the different measure. So the measure is no longer the usual Lebesgue measure. The measure is here multiplied by log x power k with this, and we prove that this function is actually, you consider this is independent of x. So this is a constant, and this constant involve the constant we just defined. You can find out here gamma xyq, and this zeta function zeta k alpha r1 q1, which is our newly defined constant. So with the help of this we have solved that even for digital divisor problems in arithmetic. So these are called divisor problem in arithmetic progressions. We still have results like Larvik. So there are many more applications. So but okay, again let me skip the proof. Proof is little bit technical. So yeah, so let me skip the proof. So let me define one more class of constant due to something called Ford and Diamond, and they have studied this kind of constant in terms of a set. For example, if you start with a set of primes and you want to define a number delta p which is of the form 1 minus 1 by p, and p is running over the set of primes, some primes, not all the primes, you can choose say 10 primes. Okay, and then they define something called gamma p. Gamma p is of the form 1 by n delta p log x, and whenever the GCD is 1, n is co-prime to all the prime factors. And then this constant is called the Diamond-Ford constant, gamma p, and they showed that these constants are very important. Why? Because whenever this function takes values at the first r prime, so this pr is the first rth prime. If this value is bigger than e power minus gamma, you can see that gamma is also appear here. So the generalized gamma for Diamond constant, if it takes value more than e power gamma, then actually Riemann hypothesis is true. So Riemann hypothesis is actually equivalent to this constant taking value more than e power gamma. So this is one of the major results towards using this gamma function attached with the set. So far we are taking the gamma function attached with the numbers. Now we have a set of primes. Okay. So this is due to Diamond and Ford, And then Diamond and Ford has proved many other results. For example, they showed that these numbers are actually takes both the values. There are infinite places, it takes gamma r plus 1 in taking more than value gamma r, and there are infinite integers, it's taking the other way. Sorry. And what we did, we generalized the idea of Diamond Ford to more general cases, and we showed that similar results are true. So let me just start with some few just notation. So we define this function x is gamma plus summation log p over this, and then we prove that L function at digital character. So this gamma chi is called the principal digital character. At S, we prove that this is actually coming out of this nice identity where this gamma k, gamma naught is appear. So gamma k, gamma naught is nothing but of these forms, limit of the summation log n power n minus this product of 1 minus p and log this function. Okay. So we prove this identity, and then we showed that actually you can define called gamma k pr, which is generalization of the Diamond constant. Diamond defined only gamma of PR. Now we are defining the kth coefficient of the Laurent function of these L functions, and is defined by this. And what we prove? We prove that this gamma k PR. So PR is that set of first r plus 1 many primes, and PR plus is first r plus 1 many primes, and PR is set of first r many primes. So when you define the gamma function on the set of r plus 1 many primes, this is related to the gamma function on the set r many primes with this relation, and with the help of this we prove this result, famous result, that gamma 1 k equal to 1 is actually the mod value is always greater than equal to this. What does that mean? That means eventually always increasing functions. The mod value is always increasing functions. What Diamond and Ford prove that they don't have, they are oscillatory, right? It can be, sometimes can be bigger than the gamma r, sometimes less than the gamma r plus 1, but we prove that it is actually eventually always increasing functions. Okay, maybe, so how much time I have? Okay, so okay, maybe I quickly I will stop. Okay, so so this was another result towards that. Maybe let me I can stop here after this, because there are so many other results, so I don't want to discuss now. Okay, and finally, so this is the sketch of the proof of these results. On just one more generalization, let me discuss. So this is this generalization is due to Goon, Shah, and Sinha, and they attach this something called the fourth diamond constant in arithmetic progression. So this R and Q, you can see that you choose all those n integer which is co-prime to the prime inside gamma, and also they are congruent to R mod Q, and then you define gamma omega RQ of these forms, and with the help of that they have shown that these results, okay, so their result is not there, this is our result. So we showed that actually in terms of this Goon, Shah, Sinha's constant also we have nice identity, and that involves this classical gamma function and the fourth diamond constant both. Okay, so so obviously then, so let me show you that what is the powerfulness of our theorem. So our theorem actually generalizes all the results which is appear in the literature. For example, if we choose k equal to 0 and the omega equal to null set phi, then our result is giving you the famous result of lemma, which appeared in 1975. And when you choose k equal to 0, r equal to 1, q equal to 1, our theorem is actually so special case is nothing but the result of Diamond and Ford, and in general when k equal to 0, our results actually nothing but the results of Goon, Shah, and Sinha. So this is the probably one of the most generalization one can do with the gamma constant attached with a set of primes, not the numbers. Okay, so these are there are several more results, so let me not discuss. Okay, so with that maybe I can stop, and thank you for listening. So let me stop here. So are there any questions? Any questions? Yes, yes, please. Identities. Huh. Identities of gamma, right? Yeah, so they are representation of gamma. Some representations are in terms of integral, some are in terms of infinite sums, but they all represent gamma constant.
And they are proven to be equivalent?
No, they are the identity of same constant, no?
But what is the rationale behind that?
Because sometimes if you need gamma, if you want to express gamma in terms of integral representation, you have more analytic properties. Sometimes if you want to know the arithmetic properties, then you need to define it in terms of the infinite sums. By arithmetic property, I mean to say that whether it has behave like irrational number or algebraic number or transcendental number, then you need more on identities involving in infinite sums. On the other hand, if you want to know about the analytic result, for example, whether a gamma function attached with some function are zero free region or not, then you need integral representations. For example, Euler constant E or pi also has different representation, right? Pi you can write down double integral of d representation, or you can use a Ramanujan identity 1 by pi sum of these, right? So they are all representing pi, but integral representation gives you more analytic results of pi. On the other hand, the infinite sums will gives you the arithmetic roots of pi, whether pi is what type of numbers. You understand?
Yeah, I understand.
Yeah. So this one, the first one is integral one. This is infinite sums representations. So these are various representations of gamma that these people have find out that you can represent gamma in terms of many ways. So this appear in, for example, you can find out some integral which involve on this function. You can find out that they are actually ended up with gamma constant. That's why you have various representation. Then you have double sum representations, and this representation is, see, the last one is very interesting. You see the Riemann zero function also appear inside the representation of gamma.
So I was just curious about the equivalence, right? Like the first one is a continuous domain, it's an integral. Second one is a discrete.
Yes, yes. So you can write down a constant in terms of integral also, the convergence of integral also, or convergence of the infinite sums also, right? As I give you the example of pi you can have a different representation, many representations actually.
That's right, but they are all equivalent.
These are,
Quantitatively equivalent.
no, by what sense you are saying equivalence?
So like when you say pi as a ratio of circumference to the, it's similar to the differential expression, right?
But suppose what about the Ramanujan identity 1 by pi equal to this double sum of zeta 2n plus, the big sums. I mean, what is the meaning of equivalence you want to say? All are in many ways you can represent pi. It can be a discrete representation or it can be a continuous representation over integrals. Same thing for gamma. So that's why gamma, in fact, probably gamma has also I think more number of representation than pi, I believe so. Okay, and every representation has some purpose. If you want to study a particular problem, you need a particular type of representations. That's why people have studied so much. In fact, these are very few I have given, and if you want to read the Lagadia's paper, you will find out many more, many like the hundreds of representations that read. So that shows that gamma is involved with many other functions, Riemann zero functions, Euler tau functions, then Gauss gamma function, then digamma functions. Whatever number theory function you can assume, even Chebyshev function also linked with gamma. So they are all linked with gamma functions. It's so fundamental. Yes. So this one, so it's all linked. Same thing like pi and E also. E also appear many places. No, this is not known. Nothing is known here. This is a famous question actually. In fact, this. Yes, yes, yes. Masterani has done some work later. Some people also call Euler Masterani's constant also. Right. Yeah, that is the definition. That is the definition. That is the way gamma defined by the Euler. Yeah, Euler defined by this. But thing is that this question was so fascinated by Hardy. So Hardy announced that whoever proved that even gamma is irrational, he will give the Oxford chair. So the Hardy was both in the Oxford chair and the Cambridge. So he was willing to give the chair of Oxford professor chair to any person who will prove irrational number even. But we have no idea. We have some idea, some results which involve gamma functions like e power gamma and some constant. With respect to some conjecture, we can prove that they are actually algebraically independent numbers. For example, pi and e power gamma are algebraically independent. If we assume some powerful conjecture, there is some conjecture. So with respect to that, these numbers are algebraically independent, and hence they are transcendental numbers. So this is known so far. Other than that, nothing is known. Another latest result is due to me and my student. We proved that these numbers has some connection with something called the Baker constant. So maybe if I get time tomorrow, I can speak about that also. Okay. So other than that, nothing is known. But this all with respect to under the assumption of some conjecture. Yeah. So many places appear. So probably the mean value or some other values of Zipf distributions, they involve gamma functions. I was checking that what are the other places other than number theory it appears. Then I find out that, for example, Gumbel distribution mean also involve gamma function. Then what is that? Information techniques, they involve gamma. So the gamma constant appear various places. That comes not only in number theory, in other field of mathematics also, even physics, statistics, many places. So in numerous places gamma appear. Okay, thank you. Okay, so. Let's thank the speaker. So, do you need this?
Yeah.
Okay, then. Okay. Maybe after, yeah. So this.
Check. Thank you so much, Dr. Tapas Chatterjee. Your valuable insights will enhance us definitely for sure. And I would like to introduce the second session speaker, Gautam Shekhar. He is a distinguished professional with a diverse, extensive background in cryptology, information security, data science analytics, and financial technology. Currently serving as an assistant professor at Madras School of Economics, India. He holds a position of postgraduate diploma in management chair and teaches various courses including mathematical statistics, statistics for economics, and probability. Gautam is actively involved in research and publication ethics, having co-taught mathematical methods for economics and information theory and cryptology. In addition to his academic role, Gautam is a founder and president of of Madras Fintech Services Private Limited, a company focused on providing innovative services to the finance, information and communication technology, and education sectors. The company of which Gautam is driving force engages in research, software development, algorithm design, financial advising, and corporate training. Notable past clients include Infineon Technology, AG Germany, and National Power Training Institute India. Gautam is also a prolific researcher with numerous peer-reviewed publications in prestigious journals and conferences. His research contributions span various aspects of cryptanalysis, including stream ciphers, hash functions, attacks on cryptographic standards. He is actively involved in academic community, serving as a member of Program Community for Security Standardization Research 2015, and contributing to various editorial boards and conferences. Beyond his academic professional achievement, Gautam is recognized for his involvement in international standard organization. He is a valued member of ISO technical community and an active contributor to ISO work from India. Gautam is a multifaceted professional excelling in academic research, entrepreneurship, and standard development. His wealth of knowledge and experiences make him a notable figure in the fields of cryptology, information security, and financial technology. We are happy and grateful to have you here, sir. The spotlight is yours.
Am I audible? Is this fine? First of all, good afternoon, and wish you all a happy new year. It's a wonderful opportunity here to meet you all. Thanks to the university and the organizers of ICMC. And before I begin, I would like to ask you about your background. So, how many of you are from a math background, just pure math? Computer science? Okay, and the rest? Numbers don't add up. So anyway, I'll try to make this rudimentary. I mean, it's obviously not going to be as math heavy as the previous presentation. Without further ado, I'll get started. Thanks for the introduction, by the way. All right, so this is on the mathematical and computational aspects of cryptology. So before I begin with the content per se, I would like you to tell me what you understand by the word cryptology or crypto. Bitcoin? Bitcoin? Yeah, fine. Where do you think we use it in our everyday lives? Email? WhatsApp? Security. So your credit cards, debit cards, even your cars use remote authentication. So crypto is everywhere, and it basically lies at the heart of information security, or InfoSec, as we commonly call it. Now, cryptology in broad terms is the science of secret communication. If I want to send a message to you, and if I do not want a malicious third-party adversary who's able to tap in on the communication channel with which we communicate, then there are two ways of doing it. One is I can hide the message itself, or I can transform the message into a form that will be unintelligible to the third-party adversary. Now, for the first one, I'll give a quick demo. is something I've written. Um, this bulletin says that the topic is applications of number theory to cryptology. My talk is obviously going to have some number theory content in it. But the title is different, so I've corrected the title. And I'll just circulate this across. Now there's this fancy little pen that I used to write something. And I just circulate this across. Please let me know if you can see something. I've corrected the title. Now, just please try with this light on. And you may pass on this pen and whatever I wrote to others. So this, we all know, I mean, it's invisible ink, and we get these pens these days. And this art of hiding a message in plain sight, from plain sight, is what is called steganography. Cryptography or cryptology deals with converting a message into a form that is unintelligible to any person, any illegitimate person who tries to eavesdrop in on the communication between legitimate parties. Now, I'll give you we use the placeholder names Alice and Bob to denote the legitimate communicating parties. Now, they have a communication channel. It could be just a simple wire between the two. We assume that this communication channel is insecure. And there is this malicious adversary, Eve, sitting in between Alice and Bob. And Eve is able to intercept and read anything that is transmitted by Alice to Bob or Bob to Alice. Now the question is, if Alice wants to transmit a message M to Bob, then what should Alice do in order to transmit it securely, which means that Eve should not be able to understand the converted M. Now, M is transformed into some form and transmitted across this insecure channel. Bob receives this and converts it back to the original message. In this, all that Eve is able to intercept is this transform message. And for this to work successfully, this transformation has to be perfect. Meaning, Eve should not be able to get any part of M or even any information about M from M prime. Now, we'll hold this for a while, and I'll tell you, I mean, we need to motivate ourselves as to why we learned this in the first place. As I told you, cryptology forms or lies at the heart of information security. So, here are some motivations to study cryptology or information security. First is, I mean, we live in this data era thanks to semiconductor and digital technology, and obviously the security of data, sensitive or confidential data getting compromised is a serious problem, one that companies face, one that government agencies face, and even the common man also faces this problem. And this problem is being, becoming increasingly frequent. Now, one example of a major security breach happened not too long back in 2017. Equifax is a credit reporting agency based out of the United States, and they held records of US citizens, Canadian citizens, and British citizens, personal data records. And a data breach that happened in 2017 exposed about nearly half of the personal data information, expose the personal data information of nearly half of the US population. And preventing these kind of security loopholes is not merely in the hands of, database administrators or network engineers. Anybody who deals with data, be it in its creation, modification, analysis, or even mere accessing, can be seen as a potential weak link in a system's security chain. And before we get to cryptology, we'll see some of these major threats that we see around in our everyday lives. Now, a statistical study found that about 33% of credit card pins, Professor Yagnanarayanan mentioned when he spoke about cryptology, he mentioned credit card pins. And about 33% of credit card pins, that is 4-digit credit card pins, fell within a small set of 61 combinations. And this percentage increased to 50 with just 426 combinations. And now, I would like this to be more interactive than me just presenting something. So can you guess the most common 4-digit pin? You are right, spot on. The most common is 1, 2, 3, 4. Any other common pins? By the way, I should have added this disclaimer at the very beginning. This is, all that I'm presenting is only for educational purposes. You should not be using this maliciously. Okay, this is being recorded, so. All right, other pins, common pins. 0000, fine. That's actually rare. People don't use 0. But the pattern is fine. What about this? Do you think it's common for people to use this? And so is why is this common? James Bond. And okay, what do you think about this one? Why do you think this is common? Do you have your mobile phones with you? The numbers 2, 5, 8, and 0 lie on a straight line, straight vertical line. So just for ease, people choose this. And this, according to this study, the least used 4-digit pin was found out to be this one. Now, because it's the least used according to this study, now don't go back and change your pin to this one. Oh, that's going to increase the frequency of, it's not going to be least anymore. So this study exposed this, surprising thing about pin numbers. Before we try to reason why some of these are common, let me ask you this. Now, I request all of you to think of a number between 0 and 9, both included. Of course, a whole number between 0 and 9. Just think, don't announce. Done? By a show of hands, I'll try to now guess what most people would have chosen. By a show of hands, how many of you thought of the number 7? You guys did the thinking? Number 3? How many of you actually thought of numbers? Fine, about 10, 20 of you thought of. 10 of you, let's say. And 7 was thought of by 3, 3 by 2, 5, majority. So there you go. So these are actually the most commonly chosen numbers according to a psychological study. So that explains why people, rarely choose some numbers as, part of their PIN numbers. So, and that also leads us to this frequency table that we have, or frequency bar graph. So 1234 is the most common pin, followed by 1111. 0000 is rarer, 1212, and then you have 7777 and 1004. And now this can be represented by a chart like this. You can see that, yellow to red represent high frequencies. So you can see this yellow line, this diagonal yellow line. And it's not surprising. So all your 0000, 1111, 2222, etc. lie on this. Now, coming to the next InfoSec threat, mobile camera and microphone hacking. Now, Apple used to have this walkie-talkie feature on their smart watches, but it had this vulnerability that allowed hackers to listen in on consumers without their explicit consent. And Zoom also had a flaw which could be exploited to trick Mac users into opening a video call, even if they hadn't uninstalled Zoom in the past. And about, again, a good percentage of the US smartphone users believed that their device was recording their conversations without their consent, according to a sort of a credible survey. Now, do you think that this phone right here could be listening in on your communication without your consent? Yes. Could it be recording, videographing you without your consent? Yes, it can.
But not in real time.
Huh?
The law does not allow it.
No, law does not allow, but you can just get a blank message, or you can get some link or something. I mean, you just click on that, or even otherwise. I mean, you may not even see that it's happening. As I'm speaking, this could be videographing me. As I'm speaking, this could be recording me without my explicit consent. Like, even I may not be aware that this is happening. And can this happen if I switch it off? Yes, it can. What is the way to preclude this? Now, the thing is, you just remove the battery. Only when you remove the battery can you ensure that your device, your mobile phone is not recording something without your consent. Now, that cannot be done, like in some phones, I mean, you do not have this option at all to remove the battery. So here are some countermeasures which you can use. So for instance, you can use as few applications or apps, as we call them, on your device as possible. So wherever possible, use a web browser instead of using or downloading an app. So Google Meet, Skype, WebEx, Zoom, all of them give you this option. So you can basically use the web version, the web client instead of your app. And of course, you have to periodically check your device permissions to use the camera, microphone, etc. And you have to also periodically update your software and firmware. Any idea what firmware is? It's also software, but the kind of software that deals with the hardware on your PC. Now, and of course, whenever required, whenever not required, you can paste a custom-made sticker. So you get these stickers that you can paste on your camera. And you can use a dummy plug to seal your microphone. And these are things that you can put to practice to avoid this problem. And of course, do you have to be worried about your phone getting hacked? Yes. Do you have to be paranoid about it? No, perhaps not. Because these kind of things happen like, very rarely, but when this happens, the kind of ramifications that it can have could be quite severe. Now, coming to the third one, heard of this before? Keyloggers? Keyloggers are usually a piece of software or hardware. If it is hardware, it looks like this one, much like your USB pen drive. And it basically records whatever you're typing. And it can do this, for instance, by, by identifying, the sounds that are created by typing. And, the thing about this, the keyloggers, is that they can be used for, obviously they can be used maliciously. They can also be used for legitimate purposes. Can you tell me one legitimate purpose for which a keylogger could be used? Yeah, that's notes, taking notes in a meeting. Parental controls. Parents want to monitor what their children are doing on their PCs. So Windows 10, for instance, has a built-in keylogger. All right. As for countermeasures, you can use anti-keylogger or antivirus software. And you can use one-time passwords or one-time pins wherever applicable. And you can also use security tokens. You have RSA tokens that you can buy from Amazon or something. So, and you have on-screen keyboards. Or you could also insert random dummy characters into your password. So suppose my password, it's obviously, what is the most common password, by the way? Password itself. So suppose my password is password. Now instead of just typing password, I could type something like PASS00WORD. Now I'm just inserting some random numbers, some random characters into my password. And every time I do this, I have to insert the random characters exactly at the same place in my password. I shouldn't change the place every time. Now, while doing this, now what you do is, after you type in your password, you use your mouse to go to that place where you inserted the random dummy characters, and then using your mouse, select those characters, press backspace, and then you enter your password. So that's something that you can use to, of course, it does not preclude the problem. It mitigates the problem to some extent. And of course, you can use handwriting or speech recognition tools. Machine learning and artificial intelligence these days are used here, and especially in advanced solutions. Okay, so this is, the last one is password fatigue, which is the fatigue caused by having to remember a large number of passwords. Gmail, Facebook, Twitter, Instagram, LinkedIn, Telegram, internet banking are PIN numbers and passwords for applications that we have on our mobile phones. There are a number of passwords that we use, or perhaps not. Some of us may use just one password for a number of applications. As they say, don't put all your eggs in a basket. So it's obviously not a good idea to have one password for several applications. So if you want to use different passwords, and if you want to generate good passwords, and if you want to secure these passwords in a vault or something, you can use a password manager where multiple passwords are stored in one repository and secured by a single password. Now, this is where, for instance, cryptology is used. But the problem here is that, the master password could be lost or compromised, and that will lead to, losing all the passwords that you have. And so a more practical thing would be to use password recovery by, via email. So you can say forgot password and you get your password. You can reset your password. But for everyday applications, this can be a little tedious. But you can use some password-less authentication methods, like you can use your fingerprint or some other biometric identifier. And some of these methods have been shown to do better than passwords on security. Some seem to be doing better when it comes to usability, but some are worse than passwords if you go by deployability. So this is according to a study that was done in 2012. It's more than 10 years back. So we don't know whether these can replace passwords going forward. Now, I already explained some of this. Now, this, whatever I told you about converting a message into an unintelligible form by Alice and reconverting that back to its original form by Bob. They are called encryption and decryption. So encryption is the process of converting a message into a garbage form, and decryption is its opposite or reverse process. Now, this encryption is done using an algorithm which is colloquially called a cipher. A cipher is an algorithm that performs encryption on Alice's side, and the same cipher performs decryption on Bob's side. And a cipher, in addition to processing, taking this message, either M or M prime as one of its inputs, takes an additional input, and that input is called key. Well, in very simple terms, the key is a number. And our aim is to secure this key, meaning this key should be, if I call it K, this key should be with Alice and Bob, but Eve should not possess this key. So that is the whole, in a very basic, setting, this is the purpose. This is what we try to do here, safeguard this key from Eve. And well, in most cases, we prefer that the same key is used by Alice and Bob, but it could be that the key that Bob uses is directly derived from the key that Alice uses. In that case, the way to derive Bob's key is something that is publicly available, or at least that's what we assume. Yeah. So ciphers are of two kinds, again, symmetric key ciphers and asymmetric key ciphers or public key ciphers. Now, symmetric key ciphers and asymmetric key ciphers are used in tandem. They are used together to secure electronic communications. And this, I told you that this key has to be with Alice and Bob, but not with Eve. As to how this key exchange takes place, your public key ciphers take care of this part. And once the key exchange is established, your symmetric key ciphers do this encryption, that is converting M to M prime, and decryption, converting M prime to M. So public key cryptography and symmetric key cryptography are used in tandem. And more about this, I think Dr. Prem will be talking about some of this maybe tomorrow. I'll just give you an overview of public key cryptography, and I'll also talk a little bit about symmetric key crypto. And if time permits, I'll talk in detail about symmetric key ciphers. Now, because this is number theory oriented, I thought of speaking more about public key ciphers. Now, this core concept of public key crypto can be understood with this problem. Try to think of how you would solve this. Now, let's say Alice wants to send a valuable object to Bob. Okay. Now, Alice has a box in which she places this valuable object. And let's say Alice and Bob have several locks with keys, but obviously not locks to each other's, not keys to each other's locks. And let's assume that this box has a locking ring that is large enough to accommodate many locks. And obviously, Alice cannot send a key in an unlocked box, and let's further assume that the box or the locks cannot be broken physically. How do you think Alice can securely exchange this valuable object or send this valuable object to Bob? You understood the problem? Alice wants to send a valuable object to Bob. Let's say a diamond ring. Now, Alice has a box. Okay, that box has a locking ring. And if you want, I have this little box here. Fine. Now, this box has a locking ring. Now, let's say that the object is inside, and Alice closes this box. Obviously, let's say Alice cannot, if Alice can directly go to Bob and give this, then the problem is solved. But Alice has to depend on, let's say, a courier to do this. Now, how can Alice secure this? Assume that this box is unbreakable. So Alice puts this object inside, and Alice has to lock it using Alice's lock, and she has the key for that lock. Now what?
Bob will lock by another key and send it to Alice. This is unlock this key. Send it to Bob again. And back to workers. Like back to workers.
Yeah, basically, but this is like going back and forth. Yeah. So, yeah, there you go. So you have this, did you understand that solution? So Alice puts her lock and sends it, gives it to the courier, and the courier takes it to Bob. Now, what does Bob do? Can the courier break it? Like, see the contents of this box? No, because the courier does not have the key to that lock that Alice put on. Now, obviously, Bob also cannot open it because Bob also does not possess any of Alice's keys. So what does Bob do now? He gets a sealed lock box. What can Bob do now? Bob simply puts his lock on top of this lock. So now the box is locked twice. Once with Alice's lock and the second time with Bob's lock. And then Bob gives it to the same courier. The courier gives it back to Alice. Now the courier cannot open it, and neither can Alice. But what can Alice do now? Open her lock. There are two locks, one of which is Alice's. So Alice opens her lock. Now there is one lock remaining, which is Bob's. Sends it back through the courier to Bob. And finally Bob gets this box with just one lock, and that's Bob's box, Bob's lock. And he has the key to that, so he can open it. So this, if you understand, you know, we'll get to the mathematical, we can say sort of mathematical counterpart of this lock and key problem. Now this is something called Diffie-Hellman key exchange. And this is basically an answer. What we see here is an answer to the question of whether we can communicate a secret in public. If you want to communicate a secret with me right now, without resorting to other means like sending a message or sending an email, assume that every communication that is going to happen henceforth is going to happen as it is happening now. Okay, like in open. Can you still communicate a secret with me? Well, the answer is yes. Let's just try this out. Now, this is where number theory is useful. Now, I request you to choose one of you. Any volunteers? It's a simple exercise. Any volunteers? Just, you have to just choose numbers and make some few computations. Okay, thanks. So just choose a number, a positive integer, and compute, you know. Yeah, just choose a positive integer alpha and compute this 6 to the alpha modulo 13. Now I'll tell you why I chose 6 and 13 in a little while. But just choose alpha, don't announce that, and compute 6 to the alpha modulo 13. Now, I'm communicating with Dr. Prem in the open. There's nothing secretive. I did not tell him about any of this beforehand. Yeah, 6 to the power alpha modulo 13. And once you're done with it, you can announce the value. 10, okay. So, Dr. Prem has computed this 6 to the alpha modulo 13. Do you all, by the way, understand modulo? There are some from the CS background, so I was wondering. This is basically the remainder you get when you divide 6 to the alpha by 13. Now, alpha is a positive integer that Dr. Prem chose. And he just, he kept that value of alpha with himself. He's not announcing that. He just computed 6 to the alpha modulo 13, and he gave me the result. Or rather, he gave us the result. And that's 10. Now, I have chosen a positive integer beta. Let's say I've already chosen it. And I've computed this 6 to the beta modulo 13. And I'm now announcing that value of 6 to the beta 10 and u to the beta modulo 13. By the way, have some of you already worked this out? 6 to the beta modulo 13 is 2. Then what is beta? So we'll write this down. So 6 to the 0 is congruent 1. 6 to the 1 is congruent 6. 6 squared is 36. So, and it's modulo 13. So you get 10. 6 cube 60, so you have 13 into 4 is 52. So this is 8, 48, and 39, so it's 9. 6 to the 5. Are you following this? I'm just computing the remainder that you get when you divide 6 to the 0 by 13, 6 to the 1 by 13, and so on, using some properties. But you can work it out the long way. Now, 9 into 6 is 54, so now the remainder is 2, and 6 to the 6, 2 into 6 is 12, yeah. 6 to the 7 is 12 into 6, 72, so that's, you have 65, 7, 42, 39, 3, 18, so 5. 5 into 6 is 30. So 13 into 2 is 4, 26. So 6 to the 11, 24, so that's going to be. So have I exhausted? Oh, 4. Yeah. So now, what is the value of beta that I chose from this? From this? No. What is the value of beta that I chose? 5. I get this. So it's 5. 6 to the 5 is congruent to modulo 13. So I chose 5. So I had actually chosen 5. So what happens now when I do 10 to the 5 modulo 13? Can anybody compute this and tell me what you get? When you divide 10 to the 5 by 13, what is the remainder you get? You can use your calculator or your phone. 9. It should be 4. So Prem, you chose 2. So that's then V is 2. So just check whether you get 4. Or you do this 10 to the 5 minus 4. Can you do that? 10 to the 5 minus 4 on your calculator. And divide that by 13 and see if it divides. 10 to the 5. Got it? 10 to the 5 minus 4. Divides. So this is what you get. 10 to the 5 minus 4 by 13 is 7692. So there you go. Now, the point I was trying to make was simple. So after this, at the end of this exercise, the both of us have actually shared a secret, and that secret is 4. It's only because I wrote this that we were able to get the values of alpha and beta. Now imagine a large prime number in place of 13. Then would we be able to get alpha or beta immediately? That's computationally, you make it computationally infeasible, then you're sure that, through this exercise, people are not going to get alpha or beta. Now, the hardness of getting alpha or beta is what is known as the discrete log problem, and it lies at the heart of securing your ciphers, which in turn is securing your electronic applications. So we were able to do this, crack the values of alpha and beta, because I wrote this. And I was able to write this because we were dealing with 13. And we chose 13 because, we chose 13 and 6 because 6 is a primitive root modulo 13. And what does that mean? You get something like this in very layman terms. Okay, so in other words, let's say you have positive integers g, a, and n. Now, if for every a such that a and n are coprime, there exists a k, a non-negative integer k, such that g to the power k is congruent a mod n, then g is a primitive root modulo n. And n needn't be a prime. Here we use a prime. Now, if it is a prime, then it must be like this. So do you see all the numbers from 1 to 12 here in this list? 1 is there, 2 is there, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. You get something like this, then you can say that 6 is a primitive root of 13. Now, you can only do this. This works when you take primitive roots, modulo n or modulo p. So, as I said, this is a very basic example of how Diffie-Hellman works. I mean, Diffie-Hellman, there are many more things to Diffie-Hellman, but this is the very basic skeletal version of Diffie-Hellman. And your entire security is kind of based on problems of this kind. The perceived hardness that is there in number theoretic problems of this kind is what keeps your applications, your devices, electronic devices, applications secure. Now, coming to symmetric key ciphers, I mean, they are based on other kinds of techniques and tools such as linear feedback shift registers, arrays, modular addition, rotation, bit rotation, XOR or exclusive OR, which is again addition modulo 2, and permutations. So, and in symmetric key ciphers, there are two types. One, we have stream ciphers, which generate pseudo-random key-based output, which is called key stream. That is XORed with the plain text to yield the cipher text. And at the decrypting end, the same thing happens. The same cipher is used. The same input goes into that, which is the key, and it produces the same key-based stream or key stream, and that is XORed with the cipher text to give you the plain text. And so I don't know whether I have time to explain how it works, but I'll give you some popular examples which you can easily look up on the internet. RC4, de facto internet standard. HC128, SNO. SNO is used to be used in your mobile phones. And the other kind is block ciphers, which basically, in which the plain text, I mean, by the way, the message here in this, the setting that I described, where Alice transforms M to M prime, M is called plain text in cryptology parlance, M prime is called ciphertext. And if you take the plain text, you partition that into blocks of fixed length and subject each block to a set of transformations on the encryption side. And then you get the ciphertext and communicate that to Bob. And what Bob does is apply the reverse transformation on the decryption side to get the plain text. So this is how a block cipher works. And popular examples include the Advanced Encryption Standard, which is the current US government standard, the Data Encryption Standard, which preceded the Advanced Encryption Standard as the US national standard, or the Federal Information Processing Standard. And then you have GHOST, which is Russian. So these are publicly available, by the way, RC4, HC128, SNO, AES, DES, GHOST, everything is like publicly available. Okay, so I said, I spoke about, I used two terms, cryptology and cryptography. Colloquially, there isn't a difference between the two. But if you see strictly, I mean, cryptology has two parts to it. So one is what we call code making. We are all familiar, I think we all watch movies, so code making should be familiar to most of us. And the other is code breaking. Code making is what is called cryptography, and code breaking is called cryptanalysis. And cryptanalysis basically exploits weaknesses in ciphers or their implementations to achieve one or more of the following. So one is to recover the secret key. The second is to recover some information about the key, or you could recover the plain text or some information about the plain text, or you could distinguish a cipher from a random signal. Now, these four may be, quite obvious. I mean, we try to recover the message, or we try to recover the secret key. This one needs a little bit more. I mean, this distinguishing a cipher from random, I don't think I'll be able to explain that here. But maybe if there is provision, like for an offline discussion, I'll be happy to talk about it. Now, in cryptanalysis, what we assume is sometimes we have a set of plain texts and their corresponding ciphertexts. most cases you are only able to intercept the ciphertext that is communicated by Alice to Bob or Bob to Alice. Now, in some cases, you can assume that you have a plain text and its corresponding ciphertext. An example is, like if there is a ship that is about to sink, the ship will obviously send out a distress signal. And that distress signal will almost always begin with 3 letters. Can you tell me what they are? SOS. SOS. So SOS, so you know that this is a distress signal, and you've successfully intercepted the encrypted version, that is the ciphertext of the distress signal, but then you have a part of that ciphertext. You know that the first 3 letters of that ciphertext would correspond to SOS. So you have the plain text in terms of the first 3 characters and the corresponding ciphertext. And using this and algorithmic weaknesses, you can try to reconstruct the remaining message, or you can try to reconstruct the key. Now that's an example of what we call known plain text attack. And you have a chosen plain text attack in which you are able to force the, one of the parties that is communicating to use a plain text of your choice. How would you do that? Now, in World War II, for instance, the Allies, they basically planted mines in the North Sea. And these, because they planted mines in the North Sea, it prodded the Germans to send out signals to their mine-sweeping ships. And these signals would contain the German word for mine, or mines, and that word, meinen, meaning mines in German. So the Allies were able to force the Germans to send out messages, encrypted messages, wherein the original message would contain the word meinen. So this is an example of a chosen plain text attack, one in which you are able to convince or force one of the legitimate communicating parties to use a message or a part of a message according to your choice. And this legitimate communicating party, let's say Alice or Bob, is going to use that message, whatever you're supplying that person with or forcing that person with, that message is going to also be encrypted. So whoever is intercepting that message will get the encrypted form or the encrypted version of that particular word or message that you're forcing the sender to send. So this is an example of a chosen plain text attack. And a chosen ciphertext attack is where the attacker is able to choose the ciphertext. Now, as to where this can practically happen, it's not an everyday occurrence, and it's not, the setting is not all that common. But this sort of attack happens, or a version of this attack happens in banking transactions. Okay, so where the attacker does not choose the ciphertext, but the attacker is not just passively listening in on the conversation, the attacker is manipulating the contents being transmitted by Alice to Bob or Bob to Alice. Now this is an example again of a chosen ciphertext attack with just this one difference, that the attacker is not forcing the ciphertext, or is not basically choosing the ciphertext. Rather he's manipulating the ciphertext that is being communicated. Now the last part of this talk is about hashing, where a hash function is simply something that compresses a message of any length into a message or a string of a fixed length. Okay, so whatever be the length of your message, the compressed version is going to be of a fixed length. Now this is used in database lookups and as checksum functions that can be used to detect or correct transmission errors. And I'll show you a quick demonstration on how you can use hash functions to ensure that if you're sending a document, let's say, to somebody, if you want to ensure that the document you sent is the same that that person received, and there's no transmission error or transmission loss that happens, then you can use a hash function. I'll show you how you can use a hash function. And these are some security properties that a hash function has to satisfy. The first, the most important, let's say, is of collision resistance, where it should be computationally infeasible to find two messages that hash or map to the same hash value. By the way, the compressed message is what is called the hash value or the digest value, and it should be computationally infeasible for you to find two messages that map onto the same hash value. And you can also, you also have to ensure that you are not able to get any of the messages that map onto a certain digest value. Now, if you are given a digest value, it should not be able for you to go back and get one of the messages that map to that digest value. So that's called pre-image resistance. And this is something that I think we can skip, second pre-image resistance. And of course, cryptanalysis, whatever I spoke about just prior to hashing, is not entirely, I mean, we do not always apply that to ciphers. We also apply these, techniques to analyze hash functions, because hash functions are also sometimes built around ciphers. So, and the cryptanalysis of a hash function typically involves finding a collision or recovering a part of a message from its corresponding hash value. And some popular examples are MD5, RIPE-MD, and SHA-3. SHA-3 is the current Federal Information Processing Standard of the United States. MD5 used to be used in many applications. It's also on your PC. And I'll show you how MD5 can be used for checksum verification. So here are some references that will conclude my talk. But before concluding, I'll just give you that demo. So here is a text file. So the message is as follows: Dear Alice, please transfer $1,000 to Mr. Bob immediately. Now, I call this, I've just put it on a text file, and I have named it hash -test. It's a .txt file. Now, what I do is I can go to this start and go to the command prompt, and now I can change the directory to the desktop where my file is saved, and there I just have to type in cert util space hyphen hash file, and then the name of that hash file, and then the name of the hash function that you want to use. I don't know if this is very clearly visible. It looks sort of blurry from there, but you see a string here, an alphanumeric string over there. What this basically means is that, this string over here is your compression of that text file. And this alphanumeric string over here is in hexadecimal, that is in base 16. So it's basically a number. You can convert it to base 10. It's just going to be a number, a fixed length number. And regardless of the file I use, I will always get my hash output to be of the same length. So meaning the number of digits or bits or whatever it is going to be the same, regardless of the size of the file that I'm hashing. Now, where is it going to be used? Now, let's say that I'm modifying this text file So I can do one of two things. So one is I can add a 0 here. Makes a lot of difference, just 1 0. And I save this. I rerun this. Do you now see the difference? Just a small change in the text file, but you get two different hash values. Do you see any part of these two hash values overlapping? Do you see any overlapping part, like with more than, say, 2 or 3 characters? No, they look completely different. Just one change. I'll make a change which is worse than this. So let this remain 1000, but I just this is worse than that. Again, any similarities between or among any of these values? Nothing. So this is something that you can use to ensure that the file you send is the file that somebody receives. Okay, so all they have to do is to check on their side as well, or you could do it on your side. Whatever it is, to ensure that two files are the same, that is two files. One is the one that you have, that you intend to send to somebody, and you send it across an insecure channel, like your internet or some other channel. Now, if you want to ensure that the contents of the file remain as they are, then you can use this to check. Now, if I converted, like, let's say I'll undo this change, and let's see what happens. Do I get the first one? Looks like the first one at least, though it's blurred. It starts like 1, 2, 3, A053 and so on. So as soon as I change it back to the original one, I see that the hash value is still the same. So now you can use this for message integrity check. So I think what is the time now?
Software is required, sir. You run the as function.
Yeah.
Is there any software required?
No, nothing. It's built in. In your PC, you have this. Most versions of Windows have. Even primitive versions of Windows, if you're having, like, say, even Windows 95 or something like that, that will have something, may not be MD5, maybe some other hash functions. But most of the latest versions, they have MD5, they have SHA-3 even, I think. SHA-256 is another hash function. I'll just very quickly show what happens with SHA-256. Now, SHA-256 is another hash function. Yeah, I'm just concluding with this. So this is what you get if you use SHA-256. You can see that the string is longer, but again, the string is of a fixed length. Okay, so no matter what the file is that I'm using, the string is going to be of the same length as this one.
Are these as functions in hexadecimal?
Now, what you get by default is in hex, but you can code it to, your choice. You can convert it to binary or whatever.
Write our code in a Word also. You use the notepad.
Yeah.
We can use
Yeah, any file, even PDF will work. So I'll conclude here. Thanks for your attention. You can ask any questions. That one? No, that's no, nothing. No, Euler's, you may, sorry? Yeah. No, it's just a multiplicative group. For this one? this one. No, it's just a primitive root, just a definition of primitive root. Yeah. No, no, no. In fact, people don't know how to find the primitive roots. There's no known. Oh, this is the Euler's. No, 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 that's not what I mean, this is just the basic definition of what primitive root is. Oh, it looks similar, obviously. Yeah. No, you have the number of primitive roots given by phi of n. That's a well-known result. But nobody knows, I mean, there is no known method to find the primitive roots. Phi of n gives you the number of. Sorry?
This one is called Artin primitive root matrix.
Yeah.
One more doubt, sir.
Sure.
Which one is better? Actually, we take model of prime number. Whether it is better or we take product of two primes. The RSA algorithm works based on product.
That's a good question. So in RSA we do that. Diffie-Hellman we don't do that. In fact, RSA, that's a very nice question. So RSA, the birth of RSA was actually motivated by this. In this, you see what is happening. Now, I thought of a number, and Dr. Prem thought of a number, and then he gave me some computed result, and I did some computation based on that. I gave him a computed result, he did a computation based on that, so it was going back and forth. Now, imagine that you are having to send an email today, or send some communication to your bank. And now let's say you are initiating some calculation, bank does something, it comes back to you, again you do something, it goes back and forth. Instead of you just typing a password and getting done with it, if you are going back and forth, imagine the time it would take, and imagine how tedious things can get. So people wanted to find a simpler way to do this without having to go back and forth. And that led to the birth of RSA. So RSA uses this, as you rightly said, the difficulty of factoring a large semi-prime into its constituent primes, but that works differently. Here we just use a prime, or we can use any number for that matter. Even a semi-prime will do, but for the sake of simplicity, it suffices if we use a prime number. So any other questions? So I thank you again.
Buses are there at 6:45. One to Madurai and one to.
Okay, sir. Thank you so much. It was a wonderful session, and we are happy and grateful to have you, sir. Participants, I request everybody to go for your lunch and come back at exactly at 2 p.m. And then for the internal participants who are inside from Kalasalingam University, 2 buses are allocated for you guys. One through the Madurai road and other through the Rajapalayam road. You can make use of the buses. Thank you so much. I request everybody to come exactly at 2 p.m.
Lunch is
No, but whatever we speak, it should be useful to you. Yeah, அது முக்கியம். நீங்க இந்த பக்கம் யாராவது எம்எஸ்சி இல்லையா? எம்எஸ்சி ப்ரோக்ராமே இல்லையா? இருக்கா? நீங்க பிடெக். சரி சரி. No, you can just say that I am so and so from Ramanujam Institute. வேற எதுவும் படிக்க வேண்டாம். இல்லை இன்னும் யாராவது வர்றாங்களா? இதை ஆஃப் பண்ணிடலாம். ரெண்டு இதுக்கு ஒன்றும் கிடையாது. நீங்கள் போய் ரூமில் ஏதாவது ரெஸ்ட் எடுக்கலாம். நான் பேச போகிறது யூஸ் இருக்காது உங்களுக்கு. ஏன்னா ஐ டோன்ட் நோ வாட் டு ஸ்பீக். ஐம் கோயிங் டு டாக் வெரி பேசிக். ஏன்னா இருக்கிறது நாளைக்கு ஐஎஸ் இருக்குது, காம்ப்ளெக்ஸ் அனாலிசிஸ் இருக்குது. போர்டு தான். என்னுடைய செஷன்ஸ் எல்லாமே போர்டு தான். நம்ம எம்எஸ்சி ப்ரோக்ராம் இருக்கா நம்மகிட்ட? எம்எஸ்சி வரலைங்களா? இல்லை பிடெக் தான் சொல்கிறாங்க. அப்படிங்களா? ஏன்னா நான் ஒன்று பேசலாம்னு நினச்சேன். இப்போ இருக்கிற பசங்களை பார்த்துட்டு கன்வர்ஜென்ஸ் இந்த மாதிரி ஏதாவது பேசலாமான்னு இருக்கேன். ஏன்னா அவங்களுக்கு ஒன்று இருக்கிறதுல பாயிண்ட் என்ன இருக்காங்க. பிள்ளைங்களுக்கு நோட் பேட் மாதிரி எழுதுறதுக்கு அவங்க இது சும்மா உட்காந்துன்னு இருந்தாங்கன்னா அது வேலைக்கு வந்துடும். ஒர்க் ஷாப்னா தென் தே நீட் டு பி ஒர்க்கிங் டுகெதர்.
நோட் பேட் பென் எல்லாம்
அப்படிதான் இருக்கணும். மேத்தமெட்டிக்ஸ் லெக்சர்ஸ் வந்து ஜஸ்ட் உட்காந்துன்னு ஏதோ கதா கால்ஷேப் மாதிரி இருந்தால் பிரயோஜனம் இல்லை. நிறைய பிள்ளைகள் சும்மா ஃபோனை பார்த்துக்கிட்டு இருக்காங்க. அந்த மாதிரி ஐ கேன் அண்டர்ஸ்டாண்ட் ப்ராப்ளம். சரி சரி சரி, தேங்க்யூ. ஆரம்பிச்சிடலாமா? சரி சரி, இல்லை சார் சொன்னாங்க. சரி சரி. I was going to talk on continuity in many spectrums, real line, R and primary, but I'm going to change that to a little bit of just to talk introduction why certain things are needed. And I'm student's background of Dilla, basically. You're free. நீங்களும் வேஸ்ட் பண்ண வேண்டிய டைம் அவருக்கு தாக்குறது நீங்க சும்மா சொல்லுங்க ஒரு ரெண்டு லைன் அதுக்கு மேல பேசுங்க.
Good afternoon to everyone. It's with a great pleasure that I stand before you today to introduce distinguished scholar and a luminary in the field of mathematics, Dr. G.P. Yuvraj sir. Dr. Yuvraj is the renowned professor specializing in Fourier analysis and complex analysis, and his contribution have left an indelible mark on academic landscape. Now, session is yours, sir. Hand over to you.
Thank you very much. Thank you very much for your kind introduction. Good afternoon to all of you. So, basically, I know mathematics is used everywhere. Is it true, false? True. So, it is an important thing. It's the soul of science now. Without that, nothing moves. So, we want to apply mathematics to solve practical problems. We look at practical problems, we model it, whatever we want to find out, we assign a variable unknown, then we form some, using the laws of physics or something, we form equations. And then we want to solve the thing that we want to find, unknown thing we want to find. That's called mathematical modeling. So basically, this is the kind of flow. So we have some problem in our end we want to solve. So we form equations, mathematical modeling. We form equations in the unknown, which we want to find. Then we use math to solve the equation. Whatever technique we learn in mathematics, we apply to solve the equation and find out. So then we get some solution here. By solving, we get a solution. Generally, we need to go back and check whether it fixes, whether it is actually satisfies our practical problem. This is one cycle. So you start with the problem, model that as an equation, solve it, find solutions, and check back whether this solution makes sense to the reality of your problem. That's generally what is done. In general, many problems from engineering and science forms a differential equation. I'm sure all of you heard differential equations, is it? Differential equations? Yes? So then the question comes, how to solve? So we come across, so for example, here are the two things. The two problems vibrating string problem. Do you know what it means? Nothing, you just fix two nails, tie up a string tight, just like a violin. You pluck it, then it oscillates. This was studied in 1747 by D'Alembert. This is called vibrating string problem. So the point is, you fix that, you let it oscillate, you want to study the oscillations of the string. You want to understand how it works. Meaning thereby trying to find out. So he came up with the equation called wave equation, which is a partial differential equation. He tried to find solutions and there were many discussions, so we will not get into that. So that is one important physical problem. Another important physical problem was heat conduction equation. Heat conduction in solids. This was done by Fourier. He studied how heat propagates in the material. Different materials he took and conducted experiments for 4 or 5 years. Then he came up with the equation called heat equation, that is also a partial differential equation. And he tried to find solutions. That's where he tried to represent functions which are periodic in terms of sines and cosines. And it is called, the series called involving sines and cosine is called what? I am sure you have seen it in your engineering, in mathematics. Yes? Series involving sines and cosines. Sine function, cosine function. Trigonometric series in general, it is called Fourier series. Given a function, you find a series involving sines and cosines. Because we understand sines and cosines very well, how they behave. So you try to represent unknown thing in terms of known functions. This is the key in mathematics. You try to understand unknown things in terms of known factors. These two problems have given rise to many concepts in analysis, pure mathematics. So many people would think pure maths is just written something as a theory and has nothing to do with that. To solve these problems, these two problems, to understand what the solution means, there are many things in analysis, even like integral, series and sequences. Many things have evolved, the concepts evolved to try to understand the solutions of these two problems. So physics contributes to lot to mathematics. In turn, mathematical techniques helps us to solve physical problems. So understanding mathematical concepts is very important. That's one thing. Now, another thing is, for any of these models, that trying to find out solutions of your model for these models, for example, in explicitly in terms of well-known functions. What are well-known functions? What are well-known functions? Constant function, right? Power functions, x power n, x square, x cube. These are power functions, well-known functions. As he points out, trigonometric functions are very well known. We know that. Algebraic functions. So there are many mathematical modeling in the real world problems. You cannot find solutions involving only these explicit functions. In which case, you have to find an approximate solution in terms of approximations. Then how do we approximate? That is the question. So the idea is, want to find solutions to a differential equation. For example, something like this, dy by dt equal to a function t comma y. Differential equations, first of all, so we want to solve this, right? But so there could be many solutions to this. For example, if I take dy by dt equal to t square, what would be my y? Let also, I want to involve them much more. Thank you very much. Thank you. Yes. What is y? No, we want, see, dy by dt is t square, but we want to know what function, when I differentiate that, we get t square. நோட்புக் இல்லையா, திறந்து வைங்க. இதெல்லாம் சும்மா என்ன கதா காலம் பேசுறது இல்லை. எடுங்க பேப்பர் எடுங்க, வேலை செய்யுங்க. No, this is a workshop. You have to work. Please do. Mathematics never comes just for sitting and listening. It's like any other sports. We have to work on it. So, what is y? யாருமே சொல்லியே, please. Yes? Did you say something? Answer? dy by dt equal to t square. Y. So the question is, so here it is, I want to differentiate something. Some of you have given me the answer that I should get this. So the question is, what should we put in there? That is the question. Correct? Is the question clear? Right. 2 power 2t 2 power 2t power 3. 2t power 3. Is that right? Differentiate. Please do. Differentiate and let's find out what we get. You have a notebook, write it out. நீங்க நோட்லாம் இல்லையா? இப்படி எல்லாம் பண்ண கூடாது. This is workshop means we have to work. Then நம்ம கதையா சொல்றோங்க. அப்படி பார்க்க கூடாது. Learning processல we have to be very active. If you differentiate 2t cube, what do you get? என்னப்பா இது? Is this true? Then there is we can talk there and you might be listening. If it is not useful to you, then what is the point? Is it not? So I want you to follow what we do. If you have questions, ask me. We will discuss. That should be the case. Please do. 6t. It's not equal to t square. We want t square, right? We want t square. What should we differentiate to t square? That is the question. Yes? T cube. T cube. Right? T cube, 3t square. So we have to make some adjustment. What do we have to do? T cube by 3. T square. So T cube by 3. What about that? Is that right still? T cube by 3 works. T cube by 3 plus 5. When you differentiate that, what do you get? Differentiate T cube by 3 plus 5. What do you get? T square. T cube by 3 by plus 10. T square. So by any constant. Okay, there are many solutions. This is a very simple differential equation. Let's put K. This is a very simple differential equation. There are many solutions. Is it not? So how does it look like? So a solution for this would look like T cube by 3. T cube by 3 will look like your function going down like that. Y equal to T cube by 3. Is that right? Right? Cube function will look like that. If I am adding, suppose y equal to T cube by 3 plus 2, how will I get the graph of this? You are adding at every t 2 units. So this will be 1, 2, so this will be going like that. If I am subtracting constant, it will be down. So it will be going like that. So by adding constants or changing constants, you have infinitely many solutions. But to our model generally, we are looking for one solution. So for which I say that I want out of all these things, I want something which goes through this point or t of 0. So this is 0, 15. I want a solution that goes through that condition. So that gives you what? We are putting, so not only we have a differential equation, we want something y of 0 equal to some y naught. This is called initial condition. A differential equation along with the initial condition is called an initial value problem. Initial value problem. Now, the following are the questions. So this is initial value problem. What should be the question now? So we have, these are all just I am writing, not anything specific, but a modeling problem. We have modeled it, that's the differential equation, our y should satisfy initial condition that should satisfy something like that. Then what should be our question? So the question is, one, is there a solution? Right? We want to find at least one solution for our model. Question is there a solution? That problem is called existence problem. Correct? Existence problem. Is there something? Then, is it unique? Is it only one? This is called uniqueness. Uniqueness problem. If your problem is such that this has a solution and it has a unique solution, then finding approximate solutions through your computer will give you a good solution, if not exact, at least approximate. Otherwise, if these two things doesn't happen, your problem could be, you could find a solution where the solution for the actual problem may be somewhere there, your approximate solution may be somewhere else. In which case your problem is called what? Ill-posed problems. Ill-posed problems. So generally, if your problem is well posed, if you are working through the computer solving systems of equations or system of differential equation, you will get whatever solution you will get. As you increase your computations, your solution will get better and better towards your solution to the problem. If it is an ill-posed problem, no matter how much you try, the answer you get may not be the required solution for your model. It's very, very important. So now, any questions so far? So the next thing is that we are looking at when we are trying to find out approximate solution. Suppose 100 is the answer for some problem. What is an approximate answer for that? 100 is the actual solution for a problem. What could be an approximate solution for that? 99, 101, it could be 50, it could be 49. It's an approximate, but it's not a good one. It is still an approximation. But so we want to get a good approximation, means our approximation should be close to the actual one. Is it not? So if you are doing some iteration on your computer and you have done 100 iterations, you got some solution, but you look at that, well, this is not very good. Maybe I should get a better solution. Then what would you do? You will increase your iterations. 100 to 200 maybe. Then you will get a better solution. So that means our approximate solutions are slowly getting closer and closer to the actual solutions. Is there any mathematical concept of idea getting closer and closer to something? No? No. So, for example, suppose we have done 50 iterations. We get a solution. So, let me call y 50. That means I have done 50 iterations and I got some function as a solution to your model. Then I have done 75 iterations. I call it y75. Then I do 150 or 200, y200, right? As we increase our iterations, our approximation should get better and better. So what kind of concept in mathematics will be useful to study these kind of things? Continuity, very good. Continuity, very good. Here we are doing iterations one at a time. 1, 2, 3, 4. Very good, sequences. I am sure all of you heard about the sequences. But we don't know where it is used, isn't it? It is used every day in all science and engineering problems. Anybody who does modeling problem, most of the engineering science problems are modeling problems. There you will have a differential equation, you linearize and get a system of equations, then use the system to solve computer iterations, then you get a solution, check whether it is meaningful. So the idea of convergence of a sequence is very important. So that's what we are going to talk today. Sequence. Okay, what is a sequence? What is a sequence? 1 by? I am sorry. Continuous order. What does it mean, continuous order? What is a sequence? I am sure all of you guys have heard. Oh, increasing values or decreasing values in a systematic way. So remember the question, what is a sequence? See, if somebody asks me what is a sequence, I say 1, 1 by 2, 1 by 3. Does this answer question? Does it answer question? Or 1, 2, 4, 6, 8. Does this answer question what is a sequence? So what is a sequence? Do you understand the question? Sequence is what? Arrangement of objects. In that array, there is a first element, second element, third element, fourth element, arrangement. It could be sequence of people, it could be sequence of trees, it could be sequence of real numbers, it could be sequence of anything you want. So sequence means it is an arrangement in an order, first, second, third, fourth. Depending on what elements you arrange, accordingly the sequence has a name. If it's a sequence of real numbers, then it is a real number sequence. Complex numbers, it's complex number. Matrices, matrices. So a sequence, so there is an order, 1, 2, 3. That means it is a function defined on first. So a sequence is a function this we denote natural numbers 1, 2, 3 onwards, right? So let me put that f is a function taking values anywhere in a set B. If your B happens to be real numbers, it's a real number sequence accordingly, right? A real sequence is a function from n to r. This is for the real numbers, r with bold letter. So generally what does it mean? So we have f of 1, f of 2, this is some value, this is some value, goes on like this. Instead of writing like this, we denote that by as x1, x2, like that. So we write a sequence of real numbers with the notation xn or any other notation we want. So generally we write that. That means where does we start, where do we go all the way, right? Okay. Now for example, so xn could be 1 by n. That means it is 1, second term is 1 by 2, third term is 1 by 3, it goes on like that. That's the sequence. It could be yn equal to minus 1 whole power n plus 1. So what is y1? 1. y2? Minus 1. Then, it goes on like this. It could be zn equal to 2 power n. In which case, we will have first term 2, 4, 8, 16, it goes on like this. Isn't it? These are some examples. Now, if we look at this is my first term, second term, third term, we keep on going, correct? Is there any term which is 0? Is there any n for which xn will be 0? Do you understand my question? x1 is what? 1. x10 is what? 1 by 10. x100 is what? 1 by 100. Is there any value n I can give so that I will get xn equal to 0? Yes? No? Anybody? So there is no value for n, xn will be 0. But however, it is getting smaller and smaller, right? Getting smaller and smaller. So how small does it get? Note that your xn is always greater than 0 for all n equal to 1, 2 and all those things. So as n goes to infinity, n gets increasing, n is 10,000, 20,000, 1 million onwards. The values are, we see it is getting smaller and smaller, right? Does it stop somewhere? Does it stop somewhere? It doesn't stop anywhere. It keeps going. But is it approaching something? Is it approaching something? Very good, very good. Why? Very good answer. Okay, so what he says is, we will come back to these sequences. He says, as n gets large, xn gets closer to 0. Does everybody agree? Does everybody agree with that? Xn gets closer to 0. How close does it get? Next question. How close does it get? We should answer that, right? We say that it is getting closer, but how close does it get? Eh? No. Somebody else said something else. What is that value after the 0? What is the minimal value? Very good, very good. This is what we should think. He says, just after the 0, whatever minimal value up to which it is getting closer. What is the value after 0? 0.111. But if you keep on putting 0 all the time, it is 0. At last, where do you stop? Even if it is infinitesimal, how close does it get? No, these are the things we should understand, because most of the time we may miss out. We just look at the definition and then go on. So he says that, how close does it get? The answer is, however close you want. However close you want. What does that mean? So here is your number line, here is your 0, this is 1 by 2, comes on closer and closer. Now, if you say that, see, this is where it is getting closer, this number is 0.0000. If keep on writing 0 forever, it is 0. So maybe I put it on like this. Well, let me stop this. Suppose I say that this is how close it gets. It doesn't go beyond that. Would you object that it is true? Meaning thereby, so this is the point, let me put, this is the point 0.001. I say that that's how close it gets, beyond that it doesn't go. Are there any points in the sequence which is below that point? What is that point? No, you tell me what it is. No, you tell me which sequence point number which is below that. No, my question is, see, these are the terms of the sequence, right? I am saying that all these terms are just stopping below, above that. You say that it is not. When you say it is not, you should give me an example which term of the sequence is below that. Do you understand the question or not? Eh? 0 to, no, any decimal value, but I want to know which term. See, 1 by 2, is it there? I am asking you, 1 is definitely not below that. 1 by 2 is not below that. 1 by 3 is not below that. Is there any point which is below that? 1 by 99, it is not below that. Eh? 1 by? Very good. You tell me like that. So, for example, 1 by 10,000. 10,000. This is nothing but x suffix 10,000. This is definitely smaller than this, so it is somewhere here. Not only this is there, but anything below that is also there. Is that right? But this is only a number I gave you. You can make smaller numbers yourself. You can find something like this happen. So this tells us that your sequence, as long as you are away from origin, there are many terms except first few finite terms, except first finite number of terms, all the other terms are close to the origin. Is that true or not? Do you understand? This happens for any positive number you choose or I choose. Not only this 0.001, you take 0.00 100,000 times and one put a 1. Even below that there are many terms, infinitely many terms. It is because of this we say that this sequence converges to 0. Any objections? Feel free. Any objections? So I am going to write that in so here it is. For any small positive number given, you give me that any small positive number, we can find terms of the sequence below that. This is what we understood so far. Is that clear? Excuse me. For any small positive number, somebody gives us, okay, you find smaller than, somebody gives me that. Then you find up to what number? See here, she went up to 10,000. Even 1,000 would have worked, isn't it? 1,000 would it have worked? No. 1,001 would have worked. 1,000 would have worked. Anything would have worked. So there is a cutoff line after which all the terms of the sequence are within that. First finitely many terms are outside, everything else inside. This works for any positive real number. So this is why for any we say that limit n going to infinity x sub n or 1 by n equal to 0 because of this. So we say that the sequence 1 by n converges to 0. No term is equal to 0, but it gets closer and closer. Close, you decide how close you want, right? Any question on this? We are going to keep this as a model. Let an be a sequence of real numbers. By the way, does every sequence converge? See, this 1 by n was lucky, simple enough, we understood. Does that mean that every sequence should approach some fixed number? Yes? What about that second example we wrote down? 1 minus 1, 1 minus 1. It does not approach any number. Yes, it is just, if you say it approaches this means what? all the terms must be, after some stage, should be close. But that doesn't happen. It jumps back. So that another sequence like 2 power n we saw, it is getting large and large without stopping. So those kind of sequences will not converge. So when we say a sequence of real numbers converge, if, when do we say it converges? There should be some real number to which it gets closer and closer. Correct? There should be some real number to which it gets closer and closer. Then only we say that this sequence converges to that. Does it make sense? Right? So, if there exists a L, if there is L in R, such that ANs all terms except first finite number of terms are close to L. See, 1 is not close to 0, 1 by 2 is not close to 0, 1 by 10 is not close to 0. But the moment you say that I want within this close, then we could find out, oh, these guys are not there, these are in there. That's how we discuss convergence. That's how the convergence concept is appearing. So we are saying that there should be a real number to which it gets closer. That means what? Once I give a, up to this much I can tolerate error. Once we say that there is a stage after which all the terms of the sequence are in that. So let us make that definition. This means close for any so here is L, here is a real line. We want the terms of the sequence are within some error. It's like when I take a shirt, dress or pant dress, you to tailor, you give instructions to the tailor, this should be 10 centimeter long, it should not be more or less. It should be 5 centimeter long, it should not be more or less. So you give specifications to the tailor, tailor cuts the cloth to stitch your shirt according to your instruction. Similarly, you decide on for any epsilon positive, you give the tolerance, how far you can tolerate your error. Then there is a stage such that, see how close you means you can measure distance between two numbers by taking modulus, subtracting each other, right? This such that modulus an minus L. This gives you an error. This is your approximation, this is your actual thing you want. So this error, how far you can tolerate? Epsilon. It could be 0.0, it could be 0.001. It all depends on how much you can tolerate. So this is less than epsilon. This may not happen for every term. This happens for all the terms after this stage, n greater than n. That means given epsilon, you form a interval, this is L plus epsilon, L minus epsilon. That gives you how far your terms could wander around. It cannot go out about that. Once you know that, then there is this n. So here an plus 1, an plus 2, something like this. It's all sitting somewhere here, getting closer and closer. That's when we say a sequence converges to L. So we say a sequence converges to L if there is an L and given that epsilon how close you want, In approximation, you need to decide beforehand how close your solution should be. In modeling, this is very needed. Then you decide how, from which term onwards you will get a better solution. And this tells you how many iterations you have to do to get a desired accuracy. That's basically what it says. Okay. Any questions on that so far? Any questions on that? Okay. Now I am going to ask you Zn equal to 1 by 3 power n. Does this sequence converge? Does this sequence converge? If it is, to what? To what value does it converge? உங்களுக்கு பேப்பர் இல்லையா எழுதுங்க. இல்லை நம்ம ஒர்க் பண்ண கிரிக்கெட் எல்லாம் விளையாடி பார்த்தா தானே கற்றுக்க முடியும். அதே மாதிரி தான் மேத்தமெட்டிக்ஸ். Does it converge? Yes, no, maybe, maybe not. அப்படி அமைதியாக உட்காந்தீங்கன்னா சைலண்ட் என்ன அர்த்தம்? சொல்லணும், தப்பா இருந்தா பரவாயில்ல. It's all right. Does it converge? Converges to what? Why?
Because that's the smallest point. That's the smallest real value we can.
No, because it is the smallest. See, for example, I can say x power, say 2 power n.
Division we are taking, sir. So it will come under this.
Oh, it is. So this is again. Look at this. 1 by 3 is the term. Next is 1 by 9, 1 by 27. That's how the sequence will be. Well, this is a part of already what we discussed. This is a part of 1 by n. 1, 1 by 2, 1 by 3, all those things. This is a part of sitting in there. This is called subsequence, and this also converges to 0. In fact, not only that, for any real number b, if the modulus is less than 1, then b power n goes to 0 as n goes to infinity. For example, b is 1 by 3 here. Previously it was 1 by n. So any real number whose modulus is less than 1, strictly less than 1, it will converge to 0. That is your exercise. Please note it down. Let's say yn equal to 1 plus 1 by 2 plus 1 by 3, sorry, 1 by 1 by 2 power n. This is also a sequence or not? Is this also a sequence or not? Yes. Does it converge to
1 by 2 power n.
1 by 2 power n is the just sum added, but converging means to a specific number, right? That's what we discussed. 1 by? No. No. No, it should be independent of n. See, 1 by n converges to 0. 1 by 3 power n converges to 0. These n's has nothing to do with that number it is approaching. So if this sequence is converging, it should be some real number, nothing to do with n. As n gets large, it gets closer and closer to that. That's all. What is the first term in the sequence? Y1. Calculate Y1, Y2, Y3. 3 values. Calculate for that, please. Calculate Y1, Y2, Y3 for those things. Y1 is what, Y2 is what, Y3 is what. Please do that. Write it out.
1 to 2 it will converge. Like up to
No. Right now let's calculate Y1, Y2 value, Y3 value. We will get us some idea what is happening. Then we will do that. Right now it looks like difficult. It's all added up. We don't know what happens as n go to infinity. What is Y1 value? Y1 value? No. Put n equal to 1. 1 plus 1 by 2. So that is 3 by 2. Is that right? Y2? Y2. That means what? This is Y1, this is Y2. So that is what? 3 by 2 plus 1 by 4. How much is it? 3 by 2 plus 1 by 4. 1.75. Is that right? So similarly you can calculate this. This is more than 1, this more than 1, this is more than 1. So it is getting larger and larger, it seems. Isn't it? For each stage as we increase, our terms are getting larger and larger. So can we still say it converges? We can say, but does it converge? Right? Does it converge? Any idea? So here is an idea. Let's see geometrically. Let me think of this as a problem like this. This is taking side 1, side 1. How much is the area of this square? Area of the square. 1 square unit, right? Let's say that that's the 1. Then I am going to add 1 by 2 of this. So I am going to add 1 here, half here. This is what you are adding, 1 by 2 to this. That's your second. Next, how much are we adding? 1 by 4. So that means this is half of this. So that's going to be 2 square. Next, what are we going to add? Next, what are we going to add? 1 by 2 cube. So half of this. 1 by 2 cube. Next. So we are going to keep going like this. So it seems that even though we are increasing, we don't seem to be getting really large. So to what value are we approaching? Very good. Is it not? No matter what happens, how many times you do, how many million times you do, next step will be this, next step will be this, next step will be this, next step will be this. It cannot go beyond that. So it looks like this is a question mark, limit n going to infinity, yn equal to, at least intuitively, என்ன அப்படியே இருக்கீங்க அமைதியா? What is the value it is approaching to? No, see, 1 by 2 added, 1 by 2 square added, keep on adding. It can never go to infinity. No, already 1 is there. First, No, you are talking about the addition, right? So this is the original starting square. You keep on adding, but it is always within this. So this will be at most 1. 1 plus 1 would be 2. So this is our guess. Is this true? Geometrically, we think that this sequence converges to 2. True or not? Agreed? No? If you have questions, let me know. Okay. Now, so here is what we do. What shall we do? So here is, so this is my yn. I multiply both sides by half. Please simplify the right hand side and let me know what you get. Please simplify the right hand side and let me know what you get. Do it quick. Please. Simplify the right hand side. Tell me what do you get. What do we get? Just multiply on the other side. Huh? Not completely, at least distribute. So this is going to be what? 1 by 2 plus 1 by 2 square. Dot dot dot. What would be the last term? 1 by 2 power n plus 1. So the previous term will be 1 by 2 power n. So this is 1 by 2 times yn. Is that right? Correct? Now let us subtract this from that. This is 1. This is 2. What do you get? 1 minus 2. That is equal to, on the left hand side, this is yn, this is 1 by 2 of yn, half of this. Then I subtract half of it, I will get 1 by 2 yn. What do we get on the right hand side? Please calculate. Calculate quick. Right hand side simplify. Huh? No. Just subtract term by term. Let's see what we get. Please do. What do we get? Huh? 1. Why? You write down, see, you subtract this quantity from this. This, subtract from that. Let me know. 1 plus. I think you are trying to just calculate up there, there's nothing wrong with that. But let's write it down. When we are in doubt, write it out. Yes? 1 by 2 into, that we have already done up to this. You subtract this from that. This is a simple 6th grade algebra. Please do. Please do. See, we hesitate to sit down and calculate. This is why we are not learning. Seriously, we have to just work it out and see what happens. It takes less time for that. What do we get?
Two answers will come, sir. Without doing 1 by 2,
No. But after doing 1 by 2 multiplication.
then 1 minus 1 by 2 power n plus 1.
Very good. Nothing, see, when you are subtracting this from this, 1 doesn't cancel. So this cancels out, right? This cancels out, and ultimately this cancels out. 1 minus, that's all it takes. This is yn, this is half yn. So from here yn equal to 2 times 1 minus 1 by 2 power n plus 1. Is that right? Multiply both sides by 2, you get yn. Yes or no? That is equal to 2 minus 1 by 2 power n. This is our yn. Now you tell me whether this sequence converges. If it does, to what value does it converge? Very good. Why? Very good. We have already observed 1 by 2 is less than 1. So as n goes to infinity, this goes to 0. So yn tends to 2 as n go to infinity. Now we have mathematically proved, previously geometrically we got some idea. Now we mathematically proved it. This sum goes to 2. Is it true? Sir, whatever it is, you say it, we accept it. No, that's not. You should really understand. If you have questions, let me know. Any questions? Okay. So, we verified our intuitive idea of geometric understanding into really mathematics. The key idea is to rewrite this in a simpler form. This is complicated. So, but this is lot less easy to understand. That was the key idea. Okay. Anybody? Questions? Okay, now what is y100? What is y100? That is 1 by 2, keep on adding until you get y by 2 power y 100, y 1000, one by 2 power 1000. So if I keep on increasing, my number of terms are going to add up, is it not? So that means what? As n increases, your number of terms on the sum gets large and large. Next we are going to see it stopped here. Next term, it is somewhere here, this 1 by 2 power 100, 1 by 2 power 101, 1 by 2 power 102, like that. So 1 plus 1 by 2, 1 by 2 square, say 1 by 2 power k, keep on adding. What is this value? What is that value? That means you keep on adding. No, see dots are there. If I didn't put sum and dot, that would be k plus 1 the next term. This dot means we are adding forever. So that means we can write this in a sum notation, summation notation. See, this can be written as 1 by 2 power 0. That's 1. 1 by 2 power 1. 1 by 2 power 2. 1 by 2. So this is 1 by 2 power j. J starts from 0 all the way to infinity. Instead of writing long notations like this, we write it in the short notation. It's called summation notation. It is an infinite series. How much was this? This is exactly what we have done. Yn plus 1, we took a limit. So this is equal to 2. So now we also understand what it means to sum infinitely many terms. This is called infinite series. In fact, for any r between 1 and minus 1, that is same as saying modulus r is less than 1. For any of that, this k equal to 0 to infinity r power k, or maybe I will use j, because my r and k's are looking similar. This series you must have seen already in your plus 2 at least. What series is called? This series has a name. Geometric series. Geometric series. When your value of these powers is strictly between minus 1 and plus 1, by the same method we have done for 1 by 2, you can show that this is equal to 1 by 1 minus r. Questions? So when we look at an infinite sum, the way we understand is, you look at the first term, you look at the first two terms added, first 3 terms added, first 10 terms added. So you look at this sequence of sums, which are called partial sums. If that sequence of partial sums converges to a number, we say that the series converges to that number. So let's make a definition. Let summation k equal to 1 to infinity ak, which is meaning to say a1, a2, this dot means you are keep adding. This is a notation only. We say this. We say the infinite series summation k equal to 1 to infinity a sub k converges if we don't know. See, if you give me 100 terms to add, we can add. If you give me 1000 terms, we can keep on adding all those things. Millions we can add. Finite number of terms we can add. But we don't have a concept of adding infinite number of terms. Even the computer cannot do it. Even the computer also has a limitation. Maybe now it is 5 trillion calculations it can do, but beyond that it will not do. So if this converges, if what we look at is terms S1, that's A1, S2, A1 plus A2, S3, A1 plus A2 plus A3. Similarly, go down, Sn equal to A1 plus A2 plus dot 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 plus An. This is called nth partial sum. This is the third partial sum. This is the second partial sum. So you go on like this. If this and Sn, this sequence, it approaches to some real number. This is called, Sn is called nth partial sum of summation k equal to 1 to a sub k. If so, by nth partial sum means we have all the partial sums, that forms a sequence. If that sequence converges to a value, then we write, in this case, we write a equal to summation k equal to 1 to infinity a sub k. Now we have given a meaning for what it means to say an infinite series converges. This is Also very important tool in your applications, in your problems in engineering and science. Either you get as a sequence of approximations or you may be doing it as a series. These two are very important no matter what you do. As long as you have some project involving mathematical model in engineering or science, you may face these kind of things. So it is very important to understand the concept of convergence of a sequence, concept of convergence of a series, infinite series. Now, anybody having questions on any of these before we proceed further? Now, see, given a series, for example, let's do an example. Summation n equal to 1 to infinity 1 by n times n plus 1. This is an infinite series. Infinite series or not? Write it out as a series, first term, second term, third term. Write it out what you get. Please write it out. This is equal to, what is the first term? 1 by 1 times 2, 1 by 2. Next term, 1 by 2 times 3, right, very good. 1 by divided by 3 times 4, it goes like this. Instead of writing all these infinite terms, we write it in the notation, that's all. Now we want to know whether this series converges or diverges. When you see an infinite series, the first question you say, does it converge? When you see a sequence, you should ask, does it converge? How do I decide? These are the questions. Now, what is the kth partial sum? Kth partial sum. Write out kth partial sum, please. So it seems that there is a tea break. We'll take a tea break and come back. By the time, please write it out. Thank you very much. என்ன பண்ண சொல்றீங்க? இல்ல நாம போர்ட்லயே பேசி ஒன்றும் ஆகாது இல்லை. Write it out, please. No pen? No, see, when we go to cricket ground, we should have bats, ball, all those things, isn't it? So similarly, wherever we are going, we should have all those equipments. Write it out. Kth partial sum. Please. This is what? You write 1 by 1 times 2, 1 by 2 times 3. Where should we stop? Where should we stop? 1 by, no, k times k plus 1. Is that right? Correct? That's the kth partial sum. If you write k equal to 1, you will get just this. K equal to 2, you will get first 2 terms. K equal to 3, you will get first 3 terms. Up to k, you go up to kth term. This is an infinite series. See, it goes on all the way. This is the kth partial sum. But still, we don't know whether this sequence will converge or not. We don't know whether this sequence converges or not. But 1 by 1 minus 1 by 2 plus, how can we write that? How can we write this as a difference of two numbers? Please pay attention. This is 1 by 2, correct? Very good. So you keep on going. At the end, 1 by k minus, is it true? Please check it out if it is true. You shouldn't write because I am writing. You shouldn't copy because I am copying. You should check it out. Is it true? Each term, does it match? Check out the first term, check out the second term, check out the third term. Is that true? Can you simplify that now? 1 minus, is that true? Why? Why? Because see, if you add these two, see that negative 1 by 2, positive 1 by 2 cancels out. The next term minus 1 by 3 plus 1 by 3 will cancel out. So it will all cancel out except 1 minus the last term. These two things are the same. This is equal to that. But this gives a way to get a simpler form. See, in mathematics this is very important. The same item, if you look at from one angle, it may look difficult. If you change your angle and look at the same thing, rewrite it in a different way, you may find a way to solve that. This is in science, it is very, very important. So, see that, so these two are one and the same. Only thing I have rewritten in a different way. But that helps us to simplify this. Now you tell me what limit k going to infinity of s sub k is equal to. What is that limit? Now you should be able to say we have done many things like that. We have s sub k on the top. We want to take k getting large and large, k going to infinity. What do you think we will get? One, very good. Because this doesn't change as k go to infinity, constant. This we know already, 1 by n goes to 0. So this also goes to 0. So this is equal to 1. So what is our conclusion? This infinite series whose partial sums converge to 1. So 1 equal to summation n equal to 1 to infinity 1 by n times n plus 1. So the point is two things. One, we have to write out and see what happens. Second, the same thing you may have to look at in different angles, whether it is mathematics or engineering or science, you may get a solution, you may get an idea instead of just looking at the same thing. So that's the idea. Okay, good. So we have proved that this series converges to value 1. Anybody having questions on that? Okay, now you tell me this one. What is the value of this infinite series? How? Look at, we have all the answers. You need to put them together and tell me what the answer is. Phone should not be there anywhere. Okay. Please, adukku enna value solunga? What is the value of this infinite series? Which is nothing but, you can write this as this is same as summation n equal to 2 to infinity 1 by n times n plus 1. This and this are one and the same. Now you tell me the answer. 1. Why? No, we should not guess. We should check it out. Any answer? 1. Look at the two series, compare them, and then tell me. No, write out this series complete. The like what I have written down, write it out. And then below that you write this out and see whether you can compare them. Very good. Not 0. We are all adding positive terms. It cannot be 0. Right? When we are keep adding positive terms, it cannot be 0. See, what is this series? This series equal to 1 by 1 times 2, 1 by 2 times 3, 1 by 3 times 4. That's that series. And now what is the value? 1 by 2. How did 1 become 1 by 2? Very good, very good. See, when you compare this series with this series, the first term is missing. You subtract on this side. So this is 1 by 2. Correct? Now I am going to ask you, yes? One by 1 square, 1 by 2 square, 1 by 3 square, அது கன்வெர்ஜ் ஆகுமா? அது கன்வெர்ஜ் ஆகுமா? The question is, does this converge? So what do you think? Yes? No? Okay, let's see this one. So we want to 1 by 2 square plus 1 by 3 square, 1 by 4 square, right? I am going to write this as 1 by 1 square as it is, correct? Okay. Now this I am going to write 1 by, instead of 2 square, I am going to write this. Is this bigger term or this bigger term? Compare these two. Which is bigger? This one is bigger, right? 1 by 2, this is 1 by 4. Just this term. Which is bigger? No, this is third. 1 by 2, right, okay. Now instead of this, I am going to have 2 times 3. Instead of 3 times 3, I am writing 2 times 3. Which is bigger now? When compared to these two terms, which is bigger? This is bigger. So for this, what should I write? For this, what should I write? 1 by 3 times 4, very good. So here, so now this is it not? This is equal. Instead of this, I am putting a bigger term. Instead of this, I am putting a bigger term. Instead of this, I am putting a... So this side series is definitely bigger than that side series. But what is this value equal to? Do we know this value? What is that value in the box? 2. Very good. Why? Very good. Well, except for that, that was 1. 1 plus 1 is 2. But we don't know what the value of this series is, but because each term is less than or equal to this is finite, this converges, so we say that this series also converges. This is called a comparison test. We compare each term, and if the larger series involving larger terms converges, then we say this also converges. No, that's what I am getting in. That's exactly what I am getting in. When your terms are positive, this works. As Professor pointed out, if it is -1, -2, it will go to negative infinity. So when we are reading theorems, we should not only look at the condition, full theorem as it is, positive terms. Okay, so this says, so we have gotten this result. N equal to 1 to infinity, 1 by n square is less than or equal to 2. And of course this non-negative. Theorem. If 0 less than or equal to an less than or equal to bn for all n equal to 1, 2, 3 onwards, or maybe let me say let 1, if summation n equal to 1 to infinity bn converges, what should be our conclusion? Summation an, not just an, summation an. So summation an also converges. What should we make second statement of? Can you make a second statement? See, this is how theorems are created. Not because somebody said as a theorem, but they look at it, okay, what more can we say on this? Can you say something? Or let me start with this. If summation n equal to 1 to infinity a n dash, then what should be in the filling in the blank? Very good, diverges. Because this is our smaller terms, if this diverges, then what? Summation Bn also diverges. This is called comparison test. Very useful. There are many tests like this for series convergence. Sorry? Not for all, but it can be after some time. But right now I am worried about that. Good point. So what professor says is that do you need this condition for all n, a1, a2? It is not that. From some point onwards, if this holds, that still you can conclude the theorem. Yes. From say 100th term onwards happens or 1000th term onwards happens, then also you can conclude the same statement. Very good. Thank you. Now, see, it is by comparison test we have proved series converges. It is one thing to prove that it converges, but actually finding the value of that is sometimes it could be really difficult, sometimes you may not be able to do it. This series sum was a famous problem in the 17th century, 18th century. Euler found the value of this series in 1735 when he was 25 years old. 31. Oh, thank you. 1731, right. So this value is equal to pi square by 6. Important number pi is connected to that, Euler. But we are not going to right now. There are ways, using Fourier series you can show that. You people know probably Fourier series. Okay, professor will give you simple proof tomorrow. Very good. There are also other ways to do it, yes. The Fourier series is not the only one. There are other ways to do it. Very good. Now, we have seen this series in the morning. What was that series? Not in the morning, in the previous section. There was a name, right? No, series. Once you put a sum, it is series. There was a name. Geometric series. Yeah, we did that, right? We did that. This converges if my x is between 1 and minus 1. X could be anything, it still converges. If I put, say for example, x equal to 0, it will converge to what? 0. This is what? Let me write it out. This is nothing but 1 plus x square. That's what you have. When I put x equal to 0, what do I get? 1. Right? You can put any one of this. Say for example, if I put x equal to 1 by 2, I will get 1 by 2, 1 by 2 square, which we have done already. So the value of this series depends on x. X could be negative 1 by 2, x could be negative 1 by 10. You can get it. We know that this was nothing but this kind of series is called power series, and it is because the powers of x is involved. It's a power series. Note that the coefficients of x power n all are 1. This is a very simple case. In general, any series n equal to 0 to infinity Cn x power n, which is equal to C0 x power 0 C1x plus C2x square dot dot dot. This is called a power series. Power series about x equal to 0. So power series may converge for some values of x, may diverge for some values of x. For example, if I put x equal to 1 there, what would I get? In this series, if I put x equal to 1, I will get 1 plus 1 plus 1. What would we get? It diverges. Partial sum is n. As n go to infinity, your sum gets unbounded. So it is important that we should know some theorems about when certain sequences are converging. That's important to use that in this situation. Suppose we have a sequence getting large and large, but getting large and large, but it doesn't go beyond certain number. Okay, so we have a sequence y1 is less than or equal to y2, y3. When your sequence satisfies this condition, what do we call them? What do we call this sequence as? What should we call this sequence as? y1 is smaller than y2, y2 is smaller than y3. Increasing sequence, that's it. So it is an increasing sequence. Increasing sequence. If Zn is a sequence Z1 greater than or equal to Z2, it is called decreasing sequence. Give me an example of a decreasing sequence. Example of a decreasing sequence. No. This is an infinite sequence. That's increasing. Decreasing. No. The negative integers from where to where? Oh, this way. That is a decreasing sequence. Very good. Any other example? Any other example of a decreasing sequence? 1 by? Very good. That's what I was expecting because we did that problem, right? So, okay. Now, we will come back to this power series after discussing this. If yn is increasing and y1 is less than or equal to m, y2 is, sir, maybe let me say that means if all the terms of the sequence are less than or equal to a fixed number. 10.5 I just put it there. In that case we say that the sequence is bounded above by 10.5. It need not be 10.5, it could be 0.5, it could be 0.3, it could be 70, something like that. So I am going to write this. So if yk is less than or equal to m for some m, or need not be even this, some m, then we say yk is bounded above y1 is bounded above by that, y2 is, y3 is, all those things. If yn is increasing and bounded above, then your sequential terms are getting larger and larger, but it never goes beyond this line, never goes beyond line. That means this is an upper bound, bounded above. If these two things happen, what can we say about this sequence? It is bounded, but then yn converges. See, if it is not bounded above sequence, it will get large and large for all values of positive numbers without any bound. It won't stop anywhere. In that case, the sequence diverges to infinity, like 2 power n or 3 power n or 2n. It diverges to infinity. But if it is bounded above, then it definitely converges to some number, not necessarily to this m, but to some number. So this is a theorem which will be useful most of the time, because you are calculating your sequence iteration on computer. It is increasing sequence, it is bounded above, then even though you cannot calculate the limit, you can say that it converges. It is very important. So that's one part of theorem. One. Decreasing and what should we add? See here, increasing and bounded above gives you this. What could you make a similar statement there? Decreasing sequence bounded below will give you convergence, and bounded below then converges. Okay? These things are useful in not only for sequences. When you deal with a series, you have to look at the sequence of partial sums. Then it will be useful, because we are keep adding terms. Then most likely, if it is all positive terms, it will be increasing, or if you are keep subtracting positive terms, it will be decreasing. Let's consider a power series. So variables there, power series. This series converges at x equal to 0, because at x equal to 0 we get the first term C0, so this is C0 plus C1x plus C2x square dot dot dot, right. When I put x equal to 0, all these things go away and I get only that. As we have seen the example, n equal to 0 to t xn, here C0 is 1, C1 is 1, C2 is 1, all the coefficients, these are called coefficients, are 1 in. This is a particular case of that. We have seen that if x is between -1 and +1, then summation n equal to 0 to infinity 1 n converges. What was the value of the series, sum of the series? We calculated that. Geometric, this is equal to this only in this range, not necessarily outside of this. For example, if we have seen that when x equal to 1, the series diverges, x equal to 1.1, series diverges. So in fact, this series diverges, see, -1 +1. It diverges for every x value here, for every x value here. If I put x equal to -0.1, -1.1, the series will diverge. -1.2 diverge. But it converges for all the values there. And the sum of the value of this series is that. Okay. So given a power series, for some x values the series may converge, for some x values the series may not converge. So here is 0. So at the center I can move 1 unit this side, 1 unit that side. For all the x values this is convergence. This is called interval of convergence. Interval of convergence. So what can you say about this series? That is also a series. Does this converge for some values of x? For any value of x, does that series converge? Let me write it out for you, that could help you. So this is equal to C0 plus C1 times x minus 2 plus C2 times x minus 2 whole square dot dot dot. Now you tell me, is there any x value for which when you substitute it, this sum gives you a finite value? That means you are not paying attention to me. Very good. When you put x equal to 2, what do you get? C0, which is a constant. Okay, very good. So this is the number line. At 2, this series converges. Then we ask immediately, okay, that's fine. Does it converge next to something? That's the question. Okay, it converges there. Can I go a little further? So meaning thereby, how far can I go this side? How far can I go this side so that this series converges in that interval with 2 as a center point? This is the problem of finding interval of convergence, or this distance is called radius of convergence. How do you calculate? Here is the method. So you calculate limit n going to infinity Cn modulus Cn plus 1 divided by Cn modulus. You take the coefficients C0, C1, you know what they are, take the modulus, make this. There are other ways also, but this would be easy for you right now. Suppose if this value equal to L, suppose that sequence converges to L. If this L value happens to be less than 1, then then let R equal to 1 by L. So first you calculate this limit, take that value, take R equal to 1 by L. Your question will be, sir, what happens if L is 0? If L is 0, I will take that to be infinity. That means it converges for all points. So R by L. Now come back to this. So we know that it converges at 2. So you go up to this 2 plus R, and this side 2 minus R. You calculate this R, that tells you how far for what points of X the series converges. This interval X minus 2 minus R, 2 plus R is called interval of convergence. But sometimes if this is L equal to 0, it will be for every X it will converge, in which case your interval of convergence is the whole real line. Otherwise you will restrict to that. And any question on this? We will take up an example to check. Any question on this? So given as infinite series, we should be able to find this R is called the radius of convergence. Or this is called radius of convergence. Let us take an example. Summation n equal to 0 to infinity 1 by n factorial x power n. Now you calculate L first, do that. I have given you the formula for calculating L. Find out what Cn's are, calculate L. There is a formula right there. Calculate L and tell me what you get. So L is equal to limit n going to infinity modulus Cn plus 1 divided by modulus Cn. You calculate and tell me. You have to tell me, otherwise I wouldn't know. Just substitute and calculate. I am not asking you to do anything else, just do that. These formulas will be useful for tomorrow's lecture also. So let us understand this. What did you get? L value. You have done that in the past, just do it and tell me. And now only you are starting. Start. Just to substitute. What is your Cn? Decide on that. Then substitute in the formula. That's all. So here what is your Cn? First we have to identify that, then only we can use this. What is your Cn? யாரோ சொல்லுங்க என்னப்பா இது What is the Cn in this case? 1 by, that's it, 1 by n factorial. See, this is variable x power n, so this must be your Cn, 1 by n factorial. So this is equal to 1 by n plus 1 factorial. Divide by 1 by n factorial. What do we get? So this is limit. That's equal to limit. First simplify the quotient and then tell me what you get. 1 by n plus 1. That's equal to 0. When L is 0, we take R as, that means this series converges, x equal to 0 it converges, and all the real numbers this side, all the real numbers here, it converges. This series converges for every real number, right? One more example. Since you know the formula, I am going to erase this off. What is your Cn? Cn is n factorial. Calculate your L. Calculate your L. L. This L is equal to this. So L equal to limit n going to infinity, Cn plus 1, what is Cn plus 1? N plus 1 factorial by n factorial, this is equal to limit n going to infinity, what does it go in there? N plus 1, which is equal to, in this case we take R 1 by L that as a 0. This means this series converges only at x equal to 0 and nowhere else. It diverges here, it diverges here. In this case we say radius of convergence is 0. So given a power series, you will have radius of convergence either 0 or finite or infinite. These are three possible cases where you can get your power series assigned to a function. suppose what do you understand of that statement? What do you understand of that statement? Given any power series, it converges at least at one point where the term becomes 0, right? Okay. But we say radius of convergence is R positive. That means what? It converges, there is at least, so if this is, so here is x equal to 0, it converges R positive, so that means up to this it goes, negative R up to this goes, for all the values the series converges. Now the question should be, oh, what happens at this endpoint and at that endpoint? Sometimes your series, when you put that value, your series may converge at that endpoint or may diverge. So accordingly you can include or not include the endpoints. Now so for any x value in this interval, this is going to give me a sum which depends on the x value, just like what we have seen summation x power n, 1 by 2, 1 by 3, anything you can put in, your value depends. So we write this series n equal to 0 to infinity a n x power n. So this, in this interval we can define a function, this depends on the x variable, we define a function f of x. When is it valid? For all the x between r and minus r. This defines a function, we define a function using this formula because it converges. If it diverges, we cannot do that, correct? So because it converges for all x and it depends, the value of the series depends on x, I am putting it as a f of x. So this f of x function is defined by this infinite series. Okay? Now, is f differentiable? Is f differentiable? Well, let us see what f of x is. See, f of x is, look like a0, a1x plus a2 x square dot dot dot. If I look at this side, if I take the derivative of a naught, what would I get? Derivative of a naught is what? 0, constant. Derivative of this would be? No, a1, 2a2 x, like that you will get. So now that, so because this side is differentiable, I am wondering whether this function is differentiable in this interval. We cannot assume it. We should know what it is. But it is a theorem. In this interval for any x, you can get the derivative by differentiating on this side term by term. It is called term by term differentiation. This implies f dash of x equal to a1 plus 2a2 x plus 3a3 x square dot dot dot. We can also write this as summation n equal to 0 to infinity n a n x power n minus 1. That's f dash of x. I haven't proved for you, but I am giving you a statement of the theorem. Now, looking back on the other side again. Okay, you are welcome. Yeah, you are welcome to go. Thank you. So, looking on the other side, right hand side again, you can again differentiate, because this series, you can term by term differentiate this again. So that means this is differentiable. So once you have a power series, your function is power series, it is infinitely differentiable. Now the question should be, sir, good. எப்போ ஆரம்பிக்குது? Another 10 minutes. Okay. Okay. I will stop maybe now, give a break and then take off. Okay. Any questions? We'll stop at this point. Tomorrow we'll pick it up. Thank you. Thank you. Thank you very much. Thank you. Good. இல்ல அந்த பசங்களுக்கு ஏதோ கிளாஸ் இருக்காட்டுங்க. பசங்களுக்கு கிளாஸ் இருக்காட்டுங்குது. பசங்களுக்கு கிளாஸ் இருக்குன்னு சொன்னாங்க. 5 மணிக்கு கிளாஸ் சார் அப்படின்னு, அதனால தான் விட்டுட்டு. Yeah, now it is cryptography. So please, கையை கழுவி வந்துடுறேன். கடத்தின் போயிடலாம இருந்தா
So I was just planning to continue from where Gautam Shekhar stopped this, today in the morning. So he was saying that there are two parties, namely this Alice and Bob, right? So you recall that, right? So they are connected via, this is a noisy or adversary can listen to whatever this Alice and Bob are talking, right? So there is a noisy channel between Alice and Bob. So he was saying that Alice wants to convey something to Bob, or Bob wants to convey something to Alice. So he was talking about what is called an encryption, right? So suppose Alice wants to convey something to Bob. He was saying that Alice could probably encrypt the and meaning I would like to call this the ciphertext C and send this to Bob, where the assumption is that both Alice and Bob have the same key K, and corresponding to this encrypt function there is a decrypt function which gives back the message M, right? So this is what he was telling in the morning. So he was saying that there are two functions, namely encrypt and decrypt. So encrypt would take the message and then create a ciphertext out of it, and then the ciphertext will be conveyed by Alice to Bob. Bob takes it and then uses the ciphertext and the key to get back the message, right? So he was saying that this assumption that both these guys have the same key K is pretty non-trivial. So how do you say, for example, I don't know Professor Ponduswamy, like we don't share any common key material between us. So how do I know that? I mean, how can I convey the message to Professor Ponduswamy? So we need to first of all do what is called this key agreement. So he was talking about this Diffie-Hellman key agreement, which would give a common key material between me and Professor. After that, we will encrypt and we will talk, right? So I just wanted to kind of pursue that thread. Like I was thinking like what to talk and so on. So I thought that would be a meaning decent enough material for about 45 minutes or so. So I thought that like why not pursue that line of thinking, right? So if you recall, like in the morning he gave an example of looking at 6 to the power alpha modulo 13, right? So he was looking at this example of 6 to the power alpha modulo 13, and we agreed upon the key, namely 4, right? So this was the common key. So my question is like, meaning this is somewhat difficult question to answer for a newcomer, but do you think this is secure? Like for example, if I want to convey something really secret to Professor, so will I use this 4 as, meaning this model of arriving at the common key? So will I use this model for arriving at the common key? So is this secure? So what do you feel about that? No, right? Because this is a very small example. So exhaustively there are only 0 to 12, there are 12 moduli. So meaning suppose sir wants to eavesdrop between what we are talking, he can exhaustively put all those values and get back the message, right? So this is a very insecure and a trivial example, and actually the entire domain of public key cryptography starts from here, right? So I was thinking of kind of telling you where do you go to kind of instantiate this. So whenever you look at, say for example, your browser, right? You just click on that. There is a lock kind of a thing in your browser, right? Whenever you do a HTTPS connection, you see a lock kind of a thing. If you just click on it, you will see various crypto terminology, namely ECDHE, ECDSA, GCM, meaning AES in counter mode, AES in GCM, and so on. So what I want to say is that, like he said, if the two parties have the common key, then life is easy. You can use many of the stream ciphers and block ciphers to get the ciphertext and get back the message. But this getting the common key is the biggest problem in cryptography. So And then he said that this is a toy example. This would give the two parties the common key, but is this secure? So you would not do this because there are hardly 12 or 13 keys possible. So you will not do it. So how do you do it? So how is it practically done in browsers? How is it practically done in various protocols which we use in the day-to-day life? I just want to kind of outline how it is done in this 40 minutes or so talk. Okay. So meaning, what do you see here? Like, what is this modulo 13? So what are these numbers 0, 1, 2 up to 12 modulo 13? So these are all the residues which you get when you divide the integers by 13, right? So what is special about this set? So I just want to ask, like, so suppose I call this set yes. So yes together with the operation star modulo 13, meaning I just want to say drop 0 for example, right? So what can you say about this set? It forms a group, right? So why is this a group? Actually, this is a starting point of the entire meaning program of instantiating your Diffie-Hellman. So how do you instantiate Diffie-Hellman? It's starting from here. So why is this a group? Are there any math people here? Okay, so why is this a group? Yeah. Yeah, meaning, okay. So what I'm asking is like, others can also try. So how do you find an inverse? Meaning, I'm just trying to write a computer program for this. Yes. So in general, suppose I have a large prime number, say 1024-bit prime number, right? So my prime is 1024 bits. So how do you find the inverse of a number? So meaning, am I allowed to use some terminology? So what is this FP, like finite field? Is anyone aware of finite fields? No, right? So okay, let us just pursue this. What I'm saying is, if you look at the set of all residues drop 0, meaning which you get by going modulo a prime, so that forms a group, right? That forms a group. It forms a cyclic group, right? And I'm asking, how do you find the inverse? I want to write a program, meaning I want to be able to write a program for doing this Diffie-Hellman. So there I need to find the inverses of elements also. So how do you find the inverse? So first of all, meaning, why is this a group? So group means various axioms, right? Associative, let us just, for associative is easy here, and then there is identity. So what is identity? And okay, so let us just, yeah, so how do you prove that it is a group? There is a set together with a binary operation, yes, it's a binary operation. Then you have associativity, you have 1. So how do you find the inverse? So the topic was number theory and cryptography. So there is both number theory here and cryptography here. Actually, it is practical. So if you meaning do a bit of investigation into your browser, so you will find that this is what is being implemented in your browser. For example, when you do a HTTPS connection. So how do you find the inverse? Say suppose I have a and P. So what do I know? So A is a residue, right? So I just drop this. A is a residue. So I want to prove that this has an inverse modulo P. How do you prove it? No, I want the algorithm. Yeah, meaning nobody else is saying. So how do you find the inverse? So what do you know about A and P? These are co-prime, right? So what does that tell us? The GCD of this and this is 1, right? So what does that tell us? There is something called the extended Euclidean algorithm, which gives you say R and S, for example, right? R times A plus S times P equal to 1. So from this, can you get the inverse of this? Right? So it's clear, right? So you know what is the inverse of A now, for example. So what I'm saying is, if you take a prime P, not 13 like what Gautam took in the morning, a large 1024-bit prime, and then look at all the moduli, non-zero moduli which you get when you divide by 13, right? You get a set. That set has a binary operation, namely multiplication modulo 13. With respect to this, it has an identity, it is associative, and we know that it has an inverse. So that forms a group, and for those of you who are familiar with the notion of what is called a finite field, the set of all non-zero elements of a finite field, if you look at that with respect to the operation of multiplication, of course modulo that prime P, that gives you a cyclic group, and it is this cyclic group where you have to go to instantiate this Diffie-Hellman, right? So today morning, Gautam Shekhar was telling that you can do Diffie-Hellman somewhere, but that somewhere is this kind of a set where you take, if I just want to write it properly, I just want to say that take a prime P, say which is 1024 bits. So this is a huge number. Like you cannot hope to make a table of inverses of all elements in this modulus, right? It's beyond the capability of any computer. You cannot go beyond 2 to the power 40, right? This is 2 to the power 1024, which is a very huge number, and meaning you cannot hope to make a table of inverses of all these moduli. So what you do is you need an effective way of inverting the elements, and that effective way is via this EEA algorithm, right? So this is what you do to find the inverse of A modulo P. So this is where you go, namely this, I just want to use a notation FP star. So this is a set of all moduli, non-zero moduli which you get when you divide by P. This set together with multiplication modulo P, this is a binary operation on this set, this forms a group. In fact, it is a cyclic group, say generated by, I want to write it multiplicatively, small g, right? So this set Fp star now is equal to g power 0, g power 1, g to the power p minus 2. So when you explicitly write down the set, these are all the elements which are there in this FP star, and this is where you go to instantiate this so-called Diffie-Hellman protocol, right? So let us just in this setting, let us just write down the protocol. So recall that there are two parties, Alice and Bob, who wish to kind of agree upon a common key, right? So Gautam Shekhar said that if they have a common key, that key can be used for encrypting their ciphertext, and I'm just saying that you cannot use the example which he had given. You should go to this kind of a world where P is a prime of a large size, and you look at the non-zero moduli, and meaning this set together with multiplication modulo P gives a cyclic group which is generated by G. Let us just look at the protocol in this setting, right? So meaning Fp star is G to the power various powers, right? And Alice and Bob now need to execute that protocol. So can anyone suggest how they do it? Alice and Bob, like for example me and Professor, so we want to talk. So we agree upon, okay, let us just fix this prime P, this particular 1024-bit prime, for which we both agree that there is this generator. Like for example, in the case of Gautam Shekhar, this P is 13 and was 6. So like that we agree upon concrete numbers for this P and for this G. And then what do we do? And then can you even tell? Yes. Yeah. Yes. So Alice chooses alpha at random, meaning in this range 0 to P minus 2, and Bob chooses beta in the range 0 to P minus 2, right? So this is secret for Alice, this is secret for Bob. So what does Alice do? She will compute G to the power alpha, right? So we said that this set forms a cyclic group. So this G power alpha is one of these numbers here. And analogously, this Bob computes G to the power beta. And again, no need to repeat, this G power beta is again a number here, right? So Alice sends G power alpha to Bob, and Bob sends G to the power beta to Alice. All right. So now, what will Alice do? Yeah. So G power beta she has received from Bob, and she knows her alpha. She computes this. On the analogously, Bob has received G power alpha from Alice, and because he has chosen this beta, he knows this beta. So what do we know about these two values? They'll be equal, right? So this is how. So this is the common key K. So if you have x to the power a whole to the power b, this we can compute as x to the power a whole to the power b or x to the power b whole to the power a. It's just meaning manipulating things in the exponent, that's all, right? So now I just want to wrap up this this finite field episode by saying that meaning because I am a cryptographer, I just want to point out. I just want to point this out. Like for example, suppose Professor and I we are talking, but there is a bad guy. So what does he see? So what does the adversary? So we call this bad guy the adversary, right? So what does the bad guy see? So he knows G. I just want to start with that. Exactly, you are right. And then he sees G power alpha and G power beta. He sees all these three values, right? So meaning for many of us, it's very counterintuitive when I say that. So what is the common key which they are agreeing upon? G per alpha beta. So the adversary knows this and this, from where he has to compute this, right? So what do you think? Is this easy or is this hard? So this is the so-called Diffie-Hellman problem. No, meaning as such, if by the yeah yeah. So this is called the Diffie-Hellman problem, and the discrete log problem, as my friend says. So here what you have is G and G power alpha. The challenge is find alpha, right? Suppose you have a algorithm for this. Suppose you have an algorithm for this, then can you solve Diffie-Hellman? Suppose I say that there is some kind of a oracle. There is a astrologer, for example, who, if you give that astrologer G and G per alpha, will give you that alpha. Then from this, can I solve this Diffie-Hellman? No, you can just take this G per beta and then raise it to the power that alpha. Done. So what it says is that if you have an algorithm for solving this discrete log problem, then you can solve this Diffie-Hellman problem. Okay. So I just want to wrap up this finite field section by saying that what Gautam Shekhar started can actually give you a concrete and secure system for arriving at a common key, but there is some work which you need to do, and that work is quantified by choosing a prime P which is large, and then recalling that our Fp star, which is the multiplicative group of the finite field of size P, is cyclic. It will be generated by, say, generated by element, say, small g. With this kind of a setup, right? So where Alice and Bob choose this P, choose this alpha, they can actually instantiate this protocol in totality. And what is involved there is Alice has to choose a random alpha in this range, Bob has to choose a random beta in this range, and then Alice computes this G per alpha, sends it to Bob, Bob computes G per beta, sends it to Alice, and it's just amounting to computing G to the power alpha beta in two different ways, right? And moreover, this protocol actually gives you a secure protocol in the sense that, meaning if you just abstract out what the adversary sees, there is no known polynomial time algorithm for the adversary who, given this G per alpha, G per beta, can compute G to the power alpha beta in polynomial time. So there is no algorithm which can be adopted by this adversary to compute this G to the power alpha beta. Okay. And if you just look at your browser, this is exactly what you will see. Okay. Yes. Yeah. 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 No, what matters? What matters? Yeah. Yes. Yes, you can do that. Yes. 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 Yeah, you'll have to work with polynomials essentially. Yes. Yes. So meaning I'll just take 2 minutes to answer your question in meaning the state of art as far as I know. So you don't do it this way. This is trivially breakable, meaning there is a sub-exponential algorithm for this due to the recent developments in what is called this index calculus. Okay, you have to go to p to the power alpha, where p is a medium size prime and alpha is some index. Yeah, so meaning large enough for that security level. You should not go to a large prime small power, even that is not secure. Medium prime large power. So only there the problem is, so there is this number field sieve which has undergone a lot of transformations. So now what was proposed say 10 years, 15 years back, no, I mean it has been vastly improved, and that could essentially break your large prime small index case, and of course this case, as well as small prime large index like 2 to the power 2 to the power 512, 2 to the power 1024, 3 to the power 399, something like that. So all those things are also not secure. So you need to have a say a 6-bit prime that raised to the power something. That is where it's called the medium prime case. So there is a small prime case, there is a large prime case, there is a medium prime case. So small and large are gone, so you have only the medium one. So that is where the state of affairs stands right now. Okay. So this is one model where you can do the Diffie-Hellman. So I was how much 10-15 minutes, 6:15, that long. Okay. Okay. So I was just thinking of giving another model where you can do this Diffie-Hellman. So I'm not just talking about the theoretical kind of a work, hand waving and etc. This is exactly what is implemented in any of our TLS protocol and hence used in any of our secure browsers. Like for example, if you just click on the, like I just said, the lock icon in your Chrome browser, for example. So you will see that this is what is implemented, like the medium prime case for the Diffie-Hellman key exchange. So like I said, this is one model. I just wanted to talk about another model. So maybe somewhat over ambitious. I don't know the background, so I just want to say that the other model is based on elliptic curves. Okay, so I just want to quickly tell you like how it is done in the elliptic curve case also. So we all know that, meaning maybe some of us know that there are something called elliptic curves, and on that you can put a group law, and you can choose elliptic curves defined over a finite field, so that computation for our protocol purposes becomes easy. And meaning you can find a cyclic subgroup of an elliptic curve, and you can make that group large enough, and you can define a generator on that, and we can play the same game. We can set the same rules for the game for Alice and Bob, right? I just want to outline the various things I said, but meaning I want to do it in a more calculus way rather than a more concrete mathematical way. All right, I just want to do the calculus, and meaning I just want to give an example and kind of hand wave saying that the theory goes through. Okay, the example I have in mind is not related to crypto at all. So I just want to fix the field Q, and I want to define the elliptic curve meaning I don't even want to call it an elliptic curve. Okay, I just want to do some calculus on this. I just want to do some calculus on this. All right. So can you tell me what do you see when you just look at this? So what I mean here is that I'll be working in this field of rational numbers, meaning needless to say, meaning this is 1, 1, 17, so the coefficients are all rational. So what do you see? Like, what is it that you see when you see this equation? So have you seen this? So what is that? Yeah, so what all comes to your mind when you see that? Sorry? Yeah, unit circle. So, meaning, I'm just asking like, what all comes to your mind? Yes, good, yes, yes sir. More. You can draw a graph of it, right? We all of us have drawn a graph of it. So, we can talk about chords, tangents, points. So, what are all the points on this? Sorry? Yeah, meaning, yeah. So, what are all the points on this? No, meaning what I'm asking is like I should do something for the rest of the time. So I just want to start somewhere here, like meaning what is that somewhere I'm not able to find out. I want to do some calculus on this. I don't want to call this anything at all. I just want to do some calculus on this. So maybe this many of us have not seen, but this many of us have seen. So what is it that we have seen here? That's what I'm asking. So sir was saying that, sorry? Symmetry, yeah, there was symmetry, yes. So we can draw a graph of it, right? And then, so what does drawing a graph mean? Yeah. Yes, I was asking, are there points on it? Origin, yes. And can you describe them? So what are those? Cos theta, sin theta, where theta ranges from this to this. You know all the points, right? You know all the points on this. So can you tell me something about this now? Yeah, this is symmetry about the x-axis. Yes. Can you give some obvious point on this? Meaning, of course, meaning obvious for me because I know the example. But so if you put x is equal to -1, two 5, yes. So I just meaning again meaning I just know the example, so I just want to call this P3. I don't want that. I want -1, -1 4. I want to take the, yeah. So what did I write down there? So if you put x is equal to -1 and y equal to 4, what do you get? The left hand side and the right hand side match, right? So meaning I'm just trying to ask you to draw a parallel between saying that the points on the unit circle, right? So this is your theta. So this point is, so these are all the points on the unit circle, right? I'm just asking you, like, I'm giving two coordinates. I mean, two pairs of coordinates. So can you see that these are lying on the curve? Are you convinced, right? So if you put x equal to -1, you get -1 cubed is -1 plus 17 is 16. Meaning, I think you need to work it out, otherwise it will be somewhat very difficult. So -1 plus 17 is 16. 16 is 4 square. So this is a point on the curve, right? If you put x equal to 2, you get 8 plus 17, that is 25, which is equal to 5 square, right? So both these points lie on the curve. Okay. Meaning I'm not very good at drawing the picture, but I think it needs to be drawn. So meaning I just put a textbook kind of a picture of this. I'm not precise, like sir was very precise. I'm not that precise. I just want to hand wave here, and meaning I will not be using the so-called Euclidean geometry which we learn in our school. So I'll just say that this is minus 1 comma, this is minus 1 comma 4 and this is 2 comma 5. I'm not drawing to scale. I'm not drawing to scale. Okay. So what I'm just giving a peek into the future. I'm just going to define a addition of points. You can add points on the unit circle, right? That's just classic trigonometry. Like that, we can add points on elliptic curves. I'm going to tell you how to add points on elliptic curves. And then the next step would be to say that the set of all points together with a different point, this forms a group under this addition law. And it will be an abelian group. And it will be a direct sum of two cyclic groups. And that one of the subgroups, you can just choose it so that you can do Diffie-Hellman on that group. Okay. So first thing is there is the set of points. Second thing is there is something called a group law. And third thing is that this forms an abelian group. Fourth thing is that you can get a cyclic subgroup out of it, and on that you can do Diffie-Hellman. So you will see that even your browsers, they use what is called this ECDHE, which stands for elliptic curve Diffie-Hellman key exchange. Okay, ECDHE. So I just said that this is my y square equal to x cube plus 17, and not drawing to scale. So this is my this is P2, this is P3, right? So what can you do with these 2 points? Just think geometry, that's all. Just think geometry. Assume that you are in Cartesian coordinates, but the points are not to the scale. Actually, meaning they are not to scale. They are not to scale. So what can you do with these 2 points? Think any obvious thing which you can do. Yeah. So I mean, of course, you know it. So anyway, just think about, like, can others have any? Sir, you have any idea? Sorry. Connect those points. Yes. So if you just join these 2 points via a straight line, right? Okay, let us just stop here. Can you tell me the equation of this line? So, meaning, can you tell the equation of this? Sorry? Yeah.
Y minus 4 divided by x plus 1 equal to 5 minus 4 divided by 5 minus 4 divided by 2 plus 1.
Y equal to mx plus c, right? So, yeah. So you get 3y minus 12 equal to x plus 1. So you get x minus 3y minus 13, right? So what are we doing? So we just said that that is a curve on which we didn't magic out. I mean, these are pretty obvious, like you just put small values and then find out. Actually, there is no algorithm for finding points on the elliptic curve. You just have to put the x coordinate at random, see whether it is a quadratic residue or not, the adjusted values, and you find a square root to find the y coordinates. That is the only way you can find points on the elliptic curve. So that is what we did here also. We magicked out 2 points, namely minus 1 comma 4 and 2 comma 5. I just said that you can add these 2 points, right? And then I drew a picture where I just drew some kind of a curve, and then 2 points P2 and P3. Sir said that let us join them, and then we joined them. Now what we have is this equation, right? This is the equation of the straight line joining P2 and P3, right? So now what happens? Now what happens is that, meaning let us go back to the picture. So we had P2 here. I just drew the P2 and P3 at convenience. So P2 and P3, suppose you join, it will go and hit the curve back again at this point P3. Why is this? So this is an elementary kind of a geometry theorem where we have a equation which is cubic and a equation which is linear, a straight line. So the number of points where they will intersect will be the product of their degrees, meaning roughly speaking, which is 3 here. So we have accounted for the 2 points. So there will be a third point of intersection. Okay? So there is a theorem which says that there is a third point of intersection. I am calling that point R. So what did we do? We joined the 2 lines and then we extended it to hit the curve again at, meaning we are guaranteed by a named theorem which says that there will be a third point of intersection, and we are calling that third point of intersection R. Alright. So can you tell me this R? You know the equation of the curve, you know the line joining them. So can you tell me what will be the third point of intersection? Yeah. So yeah. So suppose I just substitute for y. So x plus 13 equal to 3y, right? I just want to use this. So what does that give us? Y equal to this by 3. So y square is x plus 13 by 3, the whole square equal to x cube plus 17. So this gives us x square plus 26x plus 169 equal to 9x cubed plus 17 times 9 is 170 minus 17 is 153, right? 153, correct? Yeah. So what do we get? We get 9x cubed minus x square minus 26x minus 16, right, equal to 0. What did we do? We just knocked out the y from these 2 equations, right? So can you tell me the x coordinate of the third point? So we already know that minus 1 and 2 satisfy this equation. So what is the third? So suppose we just take sum of the roots equal to 1 by 9, right? Sum of the roots equal to 1 by 9 or minus? Sum of the roots equal to 1 by 9. So minus 1 plus 2 is 1 plus, I call it say z equal to 1 by 9, right? So z equal to 8 by 9, correct? Yeah, I think answers are not sure. Equal, hey, minus 8 by 9. Minus 8 by 9, right? Minus 8 by 9. So, meaning, are you able to follow what I am doing? So, what we had was there is this cubic, and then we were trying to add these 2 points. We just drew the chord which is joining these 2 points, and we said that this line which is the chord joining these 2 points will actually hit the curve again at the third point because of some named theorem. Because meaning 3 times 1 equal to 3, you have accounted only for degree 2 multiplicity, there will be a third multiplicity. So that is what we are trying to find, and then we just rearrange this to knock out this y, and we just substituted this y equal to x cube x plus 13 by 3 in this curve equation. We just rearrange, we came to a point here, right? and from here, so what does this equation tell us? It the three zeros of the three roots of this equation give you the 3 points which are there on the common line, which are common to the curve on the line, right? So this gives you the x coordinates of all the 3 points which are common to both this curve on the line. So we just use the meaning relation between the coefficients and the roots of a polynomial, right? So we know 2 zeros. The third zero we just have to find out. The sum of the zeros equal to minus of this coefficient by this, meaning minus a1 by a0, right? We just use that fact, and so what I'm saying is minus 1 plus 2 plus alpha equal to minus a1 by a0, so which is 1 by 9 in this case, so that gives alpha equal to minus 8 by 9, right? So if you just put for example here, meaning I am very bad at clearing fractions, minus 8 by 9, right, plus 13 by 3, so this is the y coordinate, namely beta, so this gives you what, right? By 27, huh? Yeah. Yeah. Okay. So what did we find? We have found the third point of intersection. We have found the third point of intersection. So I just want to, meaning, please take this for granted. So P2 plus P3 is the reflection of the third point of intersection about the x-axis. So we just found that this R is equal to minus 8 by 9 comma 109 by 27, right? I just want to reflect this point about the x-axis. Why can I do that? So just if you just look at this, it's symmetric about the x-axis. So if alpha comma beta is a point on the curve, so is alpha comma minus beta, right? So the reflection about the x-axis makes sense. So I just say that this is equal to, I just want to use the notation minus r, which essentially means that I'm reflecting about the x-axis. So in this case, I get the point minus 8 by 9 comma minus 109 by 27. Ha. So what did we do? We just started with the curve. We magicked out 2 points. I said that we can add these 2 points. The first step of the recipe is to join them. So it hits the curve again at the third point. Because of our unnamed theorem, you can find the third point of intersection. Because of the symmetry of this curve about the x-axis, meaning roughly speaking, if alpha comma beta is a point, so is alpha comma minus beta. It's just because of this square root, that's all. Meaning y square equal to something will have plus or minus roots, that's all. So third point of intersection you can find, reflect about the x-axis, that is the sum of the 2 points. Okay. So meaning I'm just rushing through it because I just want to drive home a couple of points and then wrap up before the appointed hour. So I just want to do the next exercise, namely finding 2 times P2. So I just want to do P2 plus P2. So you can say that I'm cheating because meaning, of course, meaning everybody is fixated on the diagram or the picture. So we had P2 here, P3 here. I drew it at my convenience. I joined them, extended it, made it hit the curve again, and so on. But now I'm saying find P2 plus P2. Meaning this plus is this whole this whole geometry business. Okay. So, meaning, are you going to accuse me of cheating? Because you don't, no longer have 2 points. So, what do you do? So, meaning, when I said that you have 2 points on the curve, the natural thing which occurred to us was to join them, right? Suppose you have only 1 point on the curve, what do you do? So, is it that difficult to think? You can think pictorially also. For example, meaning you forget that it is over Q. Suppose it is over R. So, you can see that there are many points on this curve. So, I am asking, like, what will you do if you have only 1 point? You can draw. So, meaning, that is why I was like saying that I was leading towards that, because meaning you forget about Q. Suppose you are over R. So, this curve has, meaning I shouldn't use curve, this equation has many zeros, many points on it. So, you can think of, meaning considering, meaning rather than just geometrically thinking about a single point, you can think about a neighborhood about it, right? So, you can keep drawing. So, for example, there is something here, there is something here. You can draw a chord, nearer, chord. So, ultimately what happens when the points come towards this P2, that becomes the tangent at that point. Meaning you just think about it geometrically. It's, meaning in the earlier case you had P2 and P3, because I drew this fixed, so we need not fixate upon it. I am just saying that if you think of this as over R, then we have many points on it. So, if you want to focus on this P2, look at the neighborhood. So, there are nice points about it. So, just draw the chords about it, and then when the points come nearer and nearer to P2, that becomes the tangent, because it's pretty, this is what we do, right? This is what we do. So, we draw the tangent at P2. Let us stop here. So, what is the tangent at P2? So, y minus 4 equal to m into, I just want to x plus 1, right? So, what is this m? 2y dy by dx. So, how do you find the slope of the tangent? Equal to 3x square, right? So, m at minus 1 comma 4 equal to 3 times x square is 1 divided by 2 times y is 4. So, which is 3 by 8. So, what is the slope of the tangent at that point? 2y dy by dx equal to 3x square. So, if you just specialize to this minus 1 comma 4, you get 3 by 8. So, that is the slope of the tangent. So, I just now have to put 3 by 8 here. So, this becomes, so help me please, 3x plus 3 equal to 8y minus 32. So, I just want to clear out y. So, 3x plus 3, oh no, I will just bring this here. So, 35, right, by 8 equal to y, correct? I just clear, meaning whatever program we did in the last case, I am just repeating it, that is all. So, only the recipe for finding the slope is different here, because we no longer have 2 points, it is just the meaning tangent that point, and tangent of the point is done. So, meaning just a quick glance, 3x plus 3 equal to 8y minus 32. So, 3y plus 35 by 8. Yeah, I think it's fine. Yeah. So what do we do now? We just put y square. So 3x plus 35 by 8 whole square equal to x cube plus 17. So this gives 9x square plus 70 times 3, 210 x plus 105, no 35 square. Sorry? 1225. Okay. By 64 equal to x cube plus 17. So you get, let us just 64 x cubed, 64 into 17 please. 64 into 17, 28, 42, 44, 64, 88, 42, 44, 8. So this becomes 1088, right? So you get 64 x cubed minus 9x square minus 210 x. I am just trying to bring this here. So plus okay. Equal to 0. So what is the magic now? What are the zeros of this? So what is the x coordinate of the third point? Sum of the zeros equal to 9 by 64, right? So we are trying to find 2 times P2, right? No. No, why? So it's just multiplicity 2, right? Sorry? Sum of the zeros I have to take. I am finding the sum of, meaning I am finding 2 times P2. I am finding 2 times P2. Yeah. So P2 is minus 1, right? So minus 1 plus alpha equal to 9 by 64. Anyway. Okay, fine. Okay, super. Okay. Plus 1. Okay. Okay. Super, yeah, super, yeah. Yeah, that's much easier. Yeah. No, but meaning algorithm. Okay, fine. I agree. Yeah. Hey, super, yeah. Are you sure? Hey, 127. Just subtraction error. 127. $137. Okay, fine. Sorry, maybe. Okay, fine. 137. So I think the answers will not match. I think the answer says 127. So anyway, so you get the recipe, right? So this is your x coordinate. You again put this x coordinate in this to get the y coordinate, and then that is the third point of intersection. Then what you do is you still reflect about the x axis, which is amounting to just finding the negative of the y coordinate. That gives you the meaning the sum of P2 and P2. All right. No, it will not work. It will not. No. The group law will not go through. I thought about this, meaning we can discuss this later, but the reflection is mandatory for getting the group law through. Only then the associativity and things like that will go through. Okay. So you have to reflect. Third point of intersection, it is guaranteed by this named theorem. Then you reflect about this x-axis. That is what is giving you the group law. Right? Point of infinity, yes. Yes. Where? No, I didn't understand your question, sorry. Oh, okay, you got the answer, fine. Huh. Yeah, yeah. Yeah. Correct, correct. 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 Correct, yeah. So this is, you just count this point twice. Yeah. Meaning it is a point which occurs with multiplicity, you say. It has multiplicity too. Yeah, so just we had a set of points, right? I just gave 2 points, but you can see that there are many points, like P2 plus P3 gave another point, 2 times P2 is giving another point, like that. So you'll have many points, all right? So because it is over Q, it can potentially have infinitely many points. But from a cryptography point of view, we will be working on a finite field. So I'm not sure how many of you are meaning familiar with this object. So finite fields are finite, meaning they will have p to the power something number of elements where p is a prime, right? So that gives you automatically a bound on the number of points on this elliptic curve, right? So x coordinate you have p to the power t choices, y coordinate you have p to the power t choices. So this product you have so many choices. So it gives you a, I mean actually the number of points on the elliptic curve will be much lesser, and that gives you a set on which you can define a well-defined composition, and there will be a identity. I'm not going to talk about it, and every point will have an inverse with respect to that group law, and the group law is actually, you can see that it is commutative. Like whether you draw the line joining P2 and P3 or line joining P3 and P2, you're going to get the same line. So it's somewhat pretty obvious that it's going to be abelian. So what we have is, we have a set of points on which we have defined a composition, and this composition actually gives you a finite group, abelian group, in the case where the underlying field is a finite field. And there is some theorems on the structures of this finite, meaning the elliptic curve on the finite field, which says that you will be able to find a nice set of subgroup of cyclic subgroup of this. So it will be a direct sum of 2 cyclic subgroups. So actually you can find a nice cyclic subgroup of this group of points, and this is another candidate where you can do the Diffie-Hellman key agreement. So I just want to just summarize this. So what we have is, so I just want to write this, but let us just leave it at that. So if you have a FQ, you have a E where y square equal to x cube plus ax plus b, where I just want to put the condition that 4a cube plus 27b square is not equal to 0, and so q equal, I just want to use p power t for example. So p is not equal to 2 and 3. So these are the conditions. So you have this curve satisfying this condition, then you have the set of points together with the so-called point at infinity. So all these things actually go into this fp e of fp power t, and what we have is the composition, like the chord, the tangent business. So with respect to this, we can add 2 points, we can add the point to itself, and the group, it actually defines a group law, meaning you can verify this sometime later maybe, where you have associativity, you have identity, you have inverse. Inverse is just reflection of the point about the x-axis, and you have also commutativity. So it is a commutative group. So this is the place where you can, meaning this is a abelian group. So with respect to the, I think this may be just terminology for you. So abelian group with respect to the so-called chord, tangent rule. And let us just, meaning to wrap up, let us just kind of look at Diffie-Hellman in this kind of a setting. And so what happens is you can find a G, which is a cyclic subgroup of this E of fp power t of prime order. Right? So this cyclic G. So usually you write it additively in this case. So what this means is that this explicitly is the so-called identity P. You just write it this way: 2P and L minus 1 times P. This is exhaustively the set of all elements in the cyclic group. So you can do what we did in the finite field case. You can mimic it here, right? So what happens is Alice will choose a alpha in the range of 0 to L minus 1, right? And she computes alpha times P. So what is alpha times P? It's P plus P plus P plus P alpha times, right? And similarly, Bob chooses a beta in the range 0 to L minus 1 and computes beta times P. So Alice sends alpha P, Bob sends beta P, and then having received beta P from Bob, Alice can compute meaning of this point, right? Similarly, having received alpha P from Alice, Bob can compute the beta fold of this. So notice that these two are same. All right? Yes. So will the discrete log be hard in that case? Oh, real numbers? No, on what field? On C, complex. So why will the discrete log be hard in that case? Not able to see. Right. No, discrete log. No, discrete log. Why is the discrete log hard in that case? Why? No, I'm not talking about 2 points. Suppose you have a point P, right? So with respect to that, you are rotating again. So the initial point and the final point are known. So can't you find the theta? No. Will the discrete log be hard? We need to work it out. Yeah. So meaning in a nutshell, genus 0 will not work. Genus 0 will not work. No, I'm saying genus. Any genus 0 will not work. You have to, yeah, the discrete log will not be hard. You have to go to genus 1. We'll talk about it later. Very good question, but yeah, we'll talk about it. We'll talk about it. We'll talk about it. Sure, yes. We'll talk about it. No, why do you want to use that? Why do you want to use that? Now, higher genus, you cannot define a group law like this. No, meaning if you can achieve what you want with just the simplest case, like meaning I'm not discouraging you, but it's just that going to higher degree equations does not give you more security. That's not the rule of thumb. Yes. No, I'm not saying anything at all. No, genus 1, it is hard. Yeah, if you do it this way, it is hard, yes. Huh. No, but he's asking x power 5, y power 5, but how does that translate to genus? Yeah. Meaning yes. No, that's not an easy question to answer. That's not an easy question to answer. Yeah. We'll talk about it. We'll talk about it. We'll talk about it. Yes. 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 You'll get a higher number of points. Yes. But meaning the calculus will not be as simple as this. This is just, I just described the calculus. So this is what you do. So if you look at that, meaning again that practical thing of clicking on that lock icon, you will see a ECDHE, for example, elliptic curve Diffie-Hellman key exchange. That will be precisely this. It will be defined on what is called the P256 curve, for example. It will be a prime of 256-bit size. On that, they would have taken a base point, namely this point P. So Alice and Bob will play this game to get the common secret key. From there, actually, a key will be derived, but essentially the crux is this, where to compute this alpha times P, as you can see, it will involve both the so-called doubling case, namely tangent case, P2 plus P2 kind of a thing, as well as the addition case, namely P2 plus P3 kind of a thing, which is the chord case. So both these things will be needed, and you need to kind of mix these operations to get this alpha times P, right, and beta times P analogously. So this is exactly what is done in the day-to-day life protocols. This is what is being done. So I just wanted to kind of, I didn't know what to talk. Sorry if you found it to be haphazard. I just want to continue the thread which Gautam Shekhar kind of started. And I just wanted to say that these are the two things which are concretely used in everyday protocols in the internet. Yeah. Yes.